Am I audible?
Yes, sir.
Okay, fine. So your OPP is on Sunday, right?
Sir, mine is done.
Oh, yours was on the previous one, right? Okay.
Yes.
Right. Uh, fine. Fine. So today is week 11, first open session, and hopefully, since again there is another batch of OPP student left, so we have got the request that if any other further session for week 11, or let's say any other session is carried on, then let's do that in the next week. So this would be the only session for this week, and hopefully I would try to discuss as much as possible of week 11. Let's see if we can complete it or not. uh, so regarding week 11, before starting the topics, I would like to state a few things. So uh, we might not need to go into very details of all the topics of week 11, and because this is kind of a, I would not say very advanced, but from our perspective, from our course perspective, we would be discussing very, I mean, discussing means the content is there. Hopefully, we would discuss a little bit more in live session, this live session also. But with respect to your examinations, there would be very specific types of question that would be expected from you guys. So, yeah, there would be some specific topics which I would discuss in the live session, where you have to put more stress, and others you can just have a basic understanding, and that shall do, that would do fine. Before, so at first I would discuss network flows, fine, and then network flows. After that, we would go into the interactability, NP class, all those concepts, because that's a fairly new thing and it's purely theoretical. So as of now, whatever we have seen in the course, that is mostly some practical. You can see an algorithm, you can apply it, and you can get a result. But the interactability and all those things are purely theoretical. Obviously they have a huge practical significance. In fact, that's why we learned them. But they are mostly practical. Sorry, they are mostly, the foundation is theoretical. So that's why I would discuss that, because it would be a little bit difficult. So after these two are done, network flow is most important in this week. After that, interactability, and then we have the LPP. Right now, LPP. Did you guys do LPP, linear programming, in any of your maths course, or uh, yeah, in this BS degree curriculum? Was it taught in any course? And someone tell
No,
where.
sir. I think I no.
Okay. So LPP is, linear programming is more of a mathematical concept, and it's so I at least I would have thought that some mathematics code should have introduced LPP, because what LPP is basically a mathematical tool to solve multiple linear equations in multiple variables. Okay, so that's what the thing is. But in PDSA, why we are encountering these LPPs? The concept is because we would see that some problem, some real life problem, right? That you can map it in the form of an LPP set of equation. I would discuss that, the motivation part. But once you map it, you can then reduce it. Now, what do I mean by reduce? Again, when I discuss interactability, it would make more sense. But just having a overview of what we would do, that's why I'm saying this. So at first, we would map a problem into LPP, and then we would see that we can somehow solve those problems even by using flow algorithms. Okay, so we might not go into that much detail, but that's the concept. So we can solve it. That's why that LPP part is given in this module, just to have a motivation to go into linear program, to go into flow algorithms and the further topics. But LPP is essentially a mathematical concept. So I would discuss LPP at last. At first, I would go into flow algorithms, then interactability, and then the motivation behind linear programming, and hopefully one problem I would discuss. But three modules LPP problems I would not discuss. If you have doubts, you can ask. In the revision session also you can ask. But those are mainly you have been given a comprehension, and from that text you have to frame equation, like in mathematics you do, right? Linear equation solving. You have to frame multiple equation and then you have to solve those equation. That's it. And solving means in this case, it's a little bit different way of solving, right? So yeah, so I would discuss one particular problem statement, but the other two you can see, because anyway they are just three different comprehension, and from these three different comprehension you have to form equations and solve it. That's the whole concept for this 11.1, 11.2, and 11.3. So one of them I would discuss. Fine, so let's start with flow algorithms at first. Acha. Can you guys see the cursor? Is it moving?
Yes, sir.
Okay, fine. So what are flow algorithms? Okay, or network flow? Right. So the topic is, so what are network flows? So so what are the types of graph algorithms that we have seen yet now? I mean, till now we have seen, at first we started with the graph representations, right? How can we represent graph in the course? Then we saw simple unweighted graph traversal. Now, what are unweighted graph traversal? Unweighted graph traversals are like BFS, DFS, those are unweighted graph traversals. And then we saw, then if we add weights to the edges of a graph, then also we can traverse the graph, and then came the shortest path, right? Before the graphs were weighted, the shortest path would be same as the shorted number of halt. That means if you have to reach from A to B, A is your source and B is your destination. On an unweighted graph, the shortest path would be the one which has least number of steps or stations in between A and B. The number of hops that you have to make between A and B should be minimum. That's what the shortest path was in an unweighted graph. As soon as you add weights on the graph edges, so the shortest path then becomes it does not have anything to do with the number of halts, but rather it becomes which is the actual shortest path in terms of the least distance, right? So that was the concept of shortest path. And then, so after we added weight, this new thing we learned, in which we learned about Dijkstra algorithm. And then we saw problems with cycles and all those things. So Bellman Ford, and then multiple pair, all pair shortest path, which is Floyd Warshall, and all those things we learned about. So shortest path notion is done. Now we will see another different kind of problem, and this is about, let's say a network is given to you, which is basically a graph, a weighted and directed graph, in which the weight given on each edge of the graph is basically the capacity, which is, or you can call it capacity, you can call it the maximum bandwidth or whatever. Basically that gives you the upper limit or the capacity that of an element or of an identity or whatever is the subject matter is, that can flow through that edge. Okay, so if we let's say we make the problem in terms of a pipeline, right? A network, a pipeline of water supply pipeline. So I would give you a graph which is essentially a network of pipelines, and these pipes are represented by edges in the graph. Okay, and the directions in the graph would tell you the direction of the flow of water through those pipelines, right? Now the capacity of each pipe in that network is given by the edge weight or the capacity weight that is given on the graph. So let's take an example. So if we have, let's say, a simple, Fine. So we have a source and a sink, and let's say some intermediate vertices ABC. Okay, so this is a graph, and each of these are pipes. So source to A is a pipe, AB is a pipe, B sink is a pipe, C sink is a pipe, right? BC is a pipe. All these are pipes, and the direction gives you the direction of the water flow. And each of these edges would have a capacity value given. Let's say this is 10, this is 8, this is 6, this is 4, this is 2, this is 11, right? Something like that, suppose. So this means that what is the maximum capacity of water that can flow from B to C, or let's say in any of the edge. So let's say the maximum capacity of water that can flow from B to C is 4, right? It cannot hold more than 4 amount of water. If it tries to pass more water, then let's say the pipe would burst or something like that. So we cannot pass more than 4 amount of water through through BC pipe. Okay. So this is a definition. Now you can map the problem to multiple cases. You can map the problem to a computer network scenario where each of these edges represent, let's say, the maximum possible, or let's say these edges represent the pathway between two routers in a computer network. And the capacity given on this edges at top, right? The edge weight or the capacity, whatever you call it, that is the maximum possible bandwidth allowed along that connection. Right? So you can map it in any possible way. So this is what we call a uh, network graph. But there are two important assumptions or rules, not assumption, rules I would say, two important rules which makes a directed graph which makes a directed graph a network flow graph. Now what are those two assumptions? And this is very important. The first assumption is there is no accumulation of the entity. Entity means this can be water, it can be your data. If it is a network graph, you can assume it the data packets which passes through the network. If it is a pipeline, water supply pipeline, you can assume the water to be the entity. Whatever entity we are talking about, which would pass through the network, right? There should be no accumulation of that entity within the network at any point. So if something is entering at point, let's say B is the word, B is this, let's take this point B. So whatever amount is entering into B must exit B. Nothing can be stored in B or A or in any of the place or inside the pipe anywhere. Nothing would be stored. It would be a flow, right? So nothing is lost and nothing is stored. You cannot store something in the between. So therefore, there is no accumulation of entity in any place of the network, in any point of the network. This is also called flow conservation. Okay. So this is very one of the important point. And other aspect is the main concept which we would now deal with, and which is saying you have to maximize the flow. Okay, so we have to maximize the flow through the network, which means I have to, so everything would start from source and everything would end into sink, right? Whatever flow is coming from the source, it would go into the sink, because uh, nothing is stored in between the graph. That means whatever is coming out of source must go into the sink, following these capacity constraints. Okay, you cannot. Okay, the third point is you have to follow the capacity constraints. Okay, so these three things, if these three things are there, on a directed weighted graph, weighted means here the weight indicates the capacity. Then we call it as a flow network. Okay. So yeah, so I was telling that everything that comes out of the source must go into the sink, and we have to maximize that how much we can pass, right? So this is the problem statement. This is the context of what we would now try to do. Now, the next thing is how can we do that? So when I say 10 is the capacity of this edge, we can pass any value which is up to 10 through this pipeline, right? Now the first thing that might come into our mind is, okay, if you have to maximize the flow, the best thing is let's take this approach that we would pass as much as possible at every point, right? So if whatever comes out, it comes out of the source, right? We cannot add anything in between. So any flow that is starting, it must start from the source. Source is the creator of the flow, or I mean it is the point where your water is getting pushed into the network, right? So therefore, let's say here 2 is the maximum capacity, so let me add 2. Here 11 is the maximum capacity, let me add 11. Okay, so this is the notion that we would follow in this graph, right? So the second part, this was capacity, the value written in blue, and we would put this bar oblique sign in front of that, and we would write in front of that 2 or 11. Now this red color number is the flow which is currently flowing through that pipeline. 2, 11, 10, these blue color numbers are the capacity of the pipeline. That means that is the maximum flow that can flow through it. And whatever is number is written in front of it in red, that indicates the current flow which is flowing through it. We know the current flow can be anything lesser than or equal to the capacity of that particular pipe. So now both these pipelines are saturated because the capacity and flow is same. So this is what we call the flow. This is what we call the flow or current flow. And this is what we call the capacity. Capacity, which is nothing but the max flow, max possible flow. Simple thing. Okay, so since we have to maximize the flow, the basic approach that we took is let's put maximum value in these two edges, which is coming out of the source. So 2 and 11. But we have to continue this 2 plus 11, that is 13 amount of water we have passed into the network. So now we have to follow the capacity constraints, and accordingly we have to pass the water forward. So let's see we can do that or not. So here 2 is there, right? So 2 is coming in this way, and then 2, yeah, 10 can hold a flow of 2. So let's put 2 over here. So 10 can flow, this 2 comes over here, so 2, 10, right? And then I came over here, I have two paths to take. Either I can go in this direction or I can go in this direction. So let's take the simple path, because our motive is anyway to put everything into the sink, and this is 8. So it can anyway hold a capacity of, a flow of 2. So let me add 2 over here. So therefore this 2 amount of water goes into the sink. That is fine. But let us see, can we pass this 11 amount of water? So we come over here, as we can see that this edge is pointing in the opposite direction, so we cannot take this. So only path is this one, right? But here the capacity is 6, so I cannot pass anything more than 6 from in the C to sink edge. So, but I have 11 amount of water. So what to do now? I cannot pass 11 amount of water. Max I can pass is 6, right? Because that's the capacity. So I pass 6. So this place where we actually passed 11, and here we are passing 6. So what does that mean? That means in between C, right, we are storing 5. 5 amount of water is getting accumulated. But we have seen that we cannot accumulate anything in the network, right? So what does that mean? That means I cannot pass a flow of 11 at this place, even though the capacity is 11. Rather, I can pass only 6. Fine. So what is the total amount of water which we can actually forward from the source to sink in this network? We see that it is 6 plus 2, 8. Right? 6 from this part and 2 from this part. So the total amount of water total amount, total water going into sink. Going into sink means which is released from the source. These are vice versa, because we are not accumulating anything in the between. So that means whatever comes from the source, that's what is forced to go into the sink. We cannot put anything in the between. So whatever comes out of the source must go into the sink. If you are not able to pass something into the sink, then you have to reduce the flow at your source. That's what we did just now. So total water going into the sink or coming out of the source, which is same, is 6 plus 2, which is 8 in this case. Right? So in this example, we saw that 8 is the amount of water going in. Now the question is it the maximum possible amount? Can we pass more than 8, or is it the maximum possible amount? That's the question. So we initially started with a max value in both the edges and kind of tried to reduce. I mean, when we are not able to pass everything to the sink, we reduced it by the maximum capacity that we had, which is 6, right? So we got this current flow. Question is, can we pass anything more than this or not? So that's where the concept of max flow comes into action. That given a flow network, a graph, what is the maximum amount of what, I mean, fluid or water, whatever, what is the maximum amount of entity that you can pass through that network? Okay, and that is what we call the what is the max flow of the network. So this would be one question. Given a network, what is the maximum flow? You have to find that integer value which is equal to the maximum possible flow that you can pass. And the second question that comes is that what is the cut? What is the minimum cut? Now I would discuss that. What is a cut? So but before going into cut, let's discuss the flow part only. So mainly two questions might come from this topic, which first one is, given a graph, what is the maximum flow? Then the second one is, given this graph, what is the minimum cut? Right? Fine. So let's address the first question at first. What is the maximum flow? Now see, the thing is, it is a small graph. In this example, still you can think in terms of your, I mean, trial and error, and you can see that whether we can pass anything more than this or not, you can figure that out pretty easily. But what happens in a big graph, or in a more complex kind of graph where there are more edges, right? So how can you solve this problem? There can be multiple paths possible, and you can pass the water from one end to another. There are multiple possible paths, right? So in that kind of scenario, it becomes very difficult to figure out without an algorithm. You cannot do it by trial and error. So we would use an algorithm which we call the Ford-Fulkerson algorithm. And we would take an example of a graph and we would run the Ford-Fulkerson algorithm now, and let's see how it works. But this is the setup of the problem. This is the context in which we would try to solve the problem. Yeah. Any question about the context? Okay, fine. So let's take a graph. This thing should be clear. The number after the oblique is the capacity and before the oblique is the flow. The flow means the current flow. Capacity is the maximum possible flow. You cannot go beyond that.
Sir, if we maximize the follow, then according to this example, it will be 8 only, right? It cannot go beyond that.
I deleted the graph anyways. I think 6, right? And then it was 2, but anything cannot go beyond there. And yeah, yeah, exactly. Yeah,
Yeah?
yeah,
Okay.
correct. Okay, so let's draw a graph. This particular graph is quite famous in many places. You can observe it. We would explain it using this graph, and then we would do the one with which is there in the slides. 13. Okay, so this is the flow graph, and now we would try to find the maximum flow that is possible from this graph, right? So this is the we would how do we apply this? It's called the Ford Fulkerson algorithm. Okay, it's Ford Fulkerson algorithm. So what we would do is initially, actually, the code, right, in your programming, if you write a program for Ford Fulkerson algorithm, what we do is we can start with, or generally it is preferred that you start with 1 value, right? So you put an initial flow of 1, right? Initial flow of 1 in both these cases, and then you proceed through the algorithm. But if you do that, it will run for some more times, right? So in order to just, since here we would mainly discuss the concept, so if it runs for two iteration, then also we would understand. So rather than starting from an initial flow of 1, we can start with an initial flow something larger than that. Okay, but before doing that, let me ask you all a question. Can you tell me what is the maximum possible flow that we can have in this network? I'm not telling you to give the answer what is the flow. I'm telling you to tell me what is the upper bound. What can you say that can you somehow say that the flow, maximum flow through this network can never be more than this amount? So what is that this amount?
24.
24, right? Yeah. So why is it 24? Because we can see that D is the sink. Oh, by the way, D is your sink and A is your source. Okay, so because we see in the sink 20 is coming and from here 4 is coming. So 20 plus 4, 24 is the maximum amount of water that can get into D, right? So this is the into the sink is 24. Okay, and so into sink, let me write it like this: into sink, max capacity is 24. Out of source, max capacity is how much? 16 plus 13, right? 16 plus 13, which is 29, right? So 29 amount of water can come out of the source and 24 amount of water can go into the sink. So a very easy way to see what can be the maximum flow is find the minimum of both of these two. Okay, so you see 24 is more or 29 is more? Obviously less, sorry, minimum. So 24 is less or 29 is less? So 24 is less. So therefore you can guarantee that whatever the max flow is, it should never be more than 24. It can be equal to 24 because that's the amount that can come into the sink. But let's say if I would have had here instead of 16, just assume here we had 6, not 16, only 6. So in that case, this number would have been 19, right? Only 19. So then, even though this input is 25, I mean, into the sink amount is 24, still we cannot have a flow more than 19. Why? Because we don't have that much capacity of water to be pushed from the source, right? So this is very important. You have to see anything that is coming into the network must go into the sink and must come out of the source. So whatever edges that are coming out of the source and whatever edges which are going into the sink, they set the upper bound for the maximum flow. Okay, fine. This is done. So we now saw that 24 is in our graph, 24 is the amount over here, and this is much more than that. So 24 can be the maximum possible flow. So since 24 is the maximum possible flow, and again I am saying you can start the algorithm from 1-1 flow also, just pass 1-1 also. This doesn't make a change. But since that would take a lot more iteration to converge, right? Your computer can do that, but for the sake of example here, we would pass something more than that. So tell me, you know that it is somewhat closer to 24, lesser than 24 or equal to 24. We have that idea. So let's start with passing 20. That's a fairly good guess. And we would see that whether we can pass 20 or not, the total inflow is 20. And if we see that we are not able to converge it to the sink, then somehow we would backtrack and pass something lesser. So at least let's start by passing 20. Okay. So just tell me two numbers. How much I pass in AF and AB. Let's start.
16 and 4.
16 and 4. You want to saturate this? Okay, fine. 16 and 4. You can pass it in any way. I am just telling. So let's say if you want to 10-10 also, we could have done anything. Doesn't matter because the algorithm would take you accordingly when you whatever flow you do. So let's start with 16 and 4. Okay. We could have passed any other values also. Okay. You don't have to saturate. You can pass 10-10. You can pass anything. I mean, any value. You can pass 1-1 also, 2-2, 3-4, whatever you want. So fine. 16 and 4. Now let's proceed. So if I have passed 16 in this edge, right? So now from FE, I have 12 over here, right? So I cannot pass the whole 16. I have to pass 12, or I mean, I pass up to 12. So what should I pass? Anything less than 12 is also okay. Tell me a number. Any number.
5.
5. Okay, nice. Let's pass 5. Okay. So 16 minus 5, 11 is left. So I must pass 11 in this way, right? There is no other edge. But see, I cannot pass 11 over here because the capacity is 10.
Okay, it is better to go 6 and 10.
Yeah. This is done. Okay. Okay, so now let's think about this 4. We have passed 4 over here. Now we can either take this 4 again at the top, or we can take the 4 like this. So which path should I take? Doesn't matter. Whatever you take.
Again 2 upwards.
2 upward. Okay.
2 upwards.
Okay.
It can distribute. It can distribute also, no? Yeah.
Anything.
And 2 here.
Anything.
Yeah.
You can do anything. Okay. 2 here. Fine. So let's see after that what happens. From here 6 is coming now. Now
no, why 2 here? You can take more than 10 and 14 is there. We can take
we have
total
passed
14
4.
also.
Oh, sorry. Yeah, we have taken 10, right? Yeah. So we have
No,
at
not
this
14, not 14. We can take 12, total 12 here.
Yeah, 14
In
is,
B2B.
14 is the capacity here. Now we have passed 2
Yeah.
at the top, so I can pass 12 here. Yeah.
12. We can take 12 also and less than 12 also, no?
Anything. Yeah.
Okay.
But if you must satisfy the constraint. So 10 plus 4, 14 is at B, right? So
Yeah,
14 must go out of B. Now I can also pass 4 here and 10 here. That's not a problem.
Correct. Got it.
Okay. So that is done. And let's say now 12 is there.
But a 9 is also coming to be. It may come out of 6.
That depends on you. If you want to pass, you can, or if you don't want to pass, you can't. Now the thing is, I wouldn't pass anything into 9. I mean, you can pass, but since here the capacity is 20, I would pass this whole 6 over here.
Okay, we will like to pass through E to D.
Yeah. But you can pass 6 from some part of the 6 from here as well. Doesn't make a change.
Yeah.
Sir, in this F to B is 10 and A to B is 4, then it will be 14, right? Which is it?
Sorry, which one?
F to B, there is a 10, right?
F to D is a 10.
and A to B is 4.
A to B is for, yeah, I think Shrikant, there is a background noise. Can you please mute when you are
Yeah,
not talking? Yeah.
Yeah, so it will be 14 by 14, right?
Okay, sorry, I was not able to hear you. Can you repeat again? There was this noise. Yeah.
F to B is 10,
Yeah.
A to B is 4. So it
A to
should
B
be
is 4. Correct.
it should be 14 by 14, right? Or we
Yeah,
say,
we are passing this 2 over here, na, on top. But then again, this has to be 8.
oh, this is taken up. Right, right. Got it, sir.
Okay, so this
Yeah.
is taken upward, but I did not write this plus 2 over here. Then it is 6 plus 2 is 8.
Yeah, got it, sir. Yeah.
Correct. This is 8 actually. Sorry.
okay. It must be added there also. Yeah.
Yeah. Okay. 8. So why I am taking this, I mean taking this path and asked you all to tell whatever some random number is to lay stress on the point. It doesn't matter in which path you take the initialization.
Sir, one thing.
Yeah.
In from A to F, 16 is coming.
Oh, just a
But-
minute. Let me complete this, then I would answer this. Okay,
Okay,
just a
okay,
minute. Hold that
okay,
question.
okay.
So we have passed 8 at this point. Now we have passed 12 in this point. Okay, so I am at C and I have 12 amount. Now let us see what we can do. Either I can pass. Okay, so I at C I have 12, but here I can only pass up to 4. So I'm passing 4 from here. Doesn't matter. So now I am left over with 8, right, out of 12. But I cannot pass 8 from this point. So only 7 can be passed. So what should I do? Let's pass 7 only. Okay, so let's pass 7 only.
No, it cannot happen. Na? One cannot.
I
we
would
have stored.
backtrack, reduce the flow.
Okay.
Okay, so let's pass 7 only. So 7 plus 4 is 11, right? Sorry, not, yeah, 11. So 1 is left over from here. So let's write 1 is left over. So now this 7 came over here and I can add this 8 plus 7, right? 8 plus 7, what it would be? 15. Now 15 can go through this 20 flow, and therefore 15 plus 4, 19 is the flow that we are getting. And but I have reduced 1, right? I have one left over. So let's reduce it at each place. So let's reduce it over here. Let's reduce it over here. So we reduce by 1 amount, and let's see from where we can reduce one more.
We can reduce.
If I 2 and 1, right? Wait, 10. Yeah, I can reduce it from here.
We can reduce at 10.
Right? 3 was there, 10, 3, 13, 12, 11, 12, 13. Yeah, correct. So I'm reduced by 3. Here initially I passed 4, now I am passing 3. So that's fine, no problem. So this is my, let us check the input of the total input amount. What it is, the total input is 16 plus 3, 19. So 19 I am putting into the network, and 15 plus 4 is also 19. So that then you can confirm that this internal calculation you have done correctly. Whatever is coming into the network from the source, right, which is 16 plus 3, that is 19. And whatever is coming into the sink, 15 plus 4, 19. If these two 19 and 19 are same, that means there is no miscalculation within this network, and you have accounted for all the diversions of the flow. So please check this. Okay, otherwise you're in the initial stage, please check after doing the initialization of the flow. Please check this source value and sink values are same or not. If they are not same, then there is some mistake in the allocation of the flow inside it. So please take this into consideration. Very, very important point. This step 1, which we just did now, the initialization of the flow, it doesn't matter in what edge you put what flow. You can start with a flow arbitrarily at the source, and then you have to follow the conservation constraints that you basically this capacity constant and conservation constant. That is, you follow the edge capacity and put a flow lesser than that, and conservation constant means keep account of the diversion. If you are taking 2 at the top, then account that here over here, do the plus 2, right? So whatever you take in from the source, propagate that till the sink. If you are getting stuck at a particular point, reduce the flow from that point to the source by that much amount. So but just have an initialization of all this, I mean initialization of the network, right? This is your step one. And again mentioning this initialization is not distinct. You can have it in any way. You can start with some other value also. You can end up with other value also. Doesn't matter. Only thing is if you are initializing with a, I mean more towards the correct answer, right? Or if you are able to initialize with a value which is passing more flow towards the sink, then the number of iteration of the subsequent algorithm, subsequent Ford-Fulkerson algorithm would be lesser. Otherwise, the number of iteration would be a far, I mean, a bit more. I could have also started the flow initialization with one value. The only difference is it would be taking much more time, but correctness wouldn't affect. So this initialization step, keep this thing in mind. There is no rocket science over here. You can start it with any possible order. Only thing to keep in mind is follow the conservation and capacity constant. If you mess up there, then the algorithm is incorrect. Okay. Yeah. Now you can ask the question.
Sir, from A to F, 16 is coming,
Yeah.
but output is 10 and 8, 18. How is it?
What is 10 and 18 means?
From A to F, 16, F to E is 8. And because only 16 will be distributed from F to E and F to B.
Okay, wait. Let me check that. 16 is coming over here. Yeah, this 2 is going now.
Uh,
16, 10 is coming
Okay.
down, right?
Okay.
6 is going over here. This 2 is coming. 6 plus 2 is 8.
But it is making like a cycle also, but then the 2 is coming and 10 is going again. It will,
Yeah.
how it will go to B to C?
Where B2C?
This cycle will do not have any effect on this.
There is no, we don't have any restriction with cycle in flow network. You can have cycles and everything.
Okay.
There is no problem. This is a pipeline, in a real life pipeline.
Okay. Got it.
Okay.
13 is
Just-
13 is the capacity, right. Only
Right.
3 is coming, it will go to, yeah, I got it. Thank you.
Fine. Okay. So
Yeah.
yeah. So this is the whole thing. Once you check this input is same, na? That's why I said you don't have to worry. Once you check this 16 plus 3 is equal to this 15 plus 4. If this is same, then you can be sure that your calculations are correct. You don't have to worry about anything. Okay. And if the capacity and flow values are under consideration, that is flow is less than the capacity in all the pipeline and your input value is same as the output value, then your initialization step is correct. Fine. So now let's this is my step one. So step one is initialize the network with a random but correct flow. Random is allowed. You can take any random value. That's what I was saying, but it should be correct. Correct means it should be propagated properly, right? It should follow the logic of conservation and capacity. Okay. Now then, therefore, this is done. Step one is done. Step two is now, and in fact, this is the core of our Ford-Fulkerson algorithm, which is draw the residual graph. Please pay attention in this step because I don't think we have these steps very clearly, explicitly stated in the lecture. Okay, it's there in the lecture, but not very explicitly stated. But in order to solve the algorithm, you would need it. So now what is a residual graph? See, let's come back to the motive. What was our motive of coming into this problem? That we want to maximize the flow. Now, how can we do that? The algorithm says there can be situations where you are passing more water through a pipe, right? But because you are passing that water through a pipe at some particular stage, at a later stage, you might lose an opportunity to attract more water through another part which had higher capacity. Okay. So basically what I'm trying to say is every time if you just go on saturating a pipe.
What did you tell, sir? Again, once
Yeah,
again.
I'm telling, just think that just keep this thing in mind, that every time if your motive is to maximize the flow through a particular pipeline, that is, you saw your pipeline with capacity 12, so you initially, I mean, just by seeing it, you decided, okay, I would pass 12 flow through it. Every time you see a pipe, you try to pass as much water through that pipe as possible. If you are following this strategy, a greedy kind of strategy, then you would not get the correct result. You might not get, not always, you might not get the correct result. Okay, it has been proved, you might not get the proper maximum flow. So the thing is, there can be some situation whereby passing lesser flow through a pipe and would help you in long run to get a higher flow. Why lesser flow through a pipe? So let me give you an example. Uh, mm, let's say in this graph, is it possible? Is it happening? Okay, let's say, okay, don't go into example. What I'm trying to say is that don't always think that if you saturate a pipe, okay, if you saturate a pipe just as soon as you see it, you would get always higher flow. The greedy approach does not work over here. Okay, and that is the whole basic of Ford-Fulkerson algorithm. Then this residual graph that we are talking about, what this graph is basically, it would allow us to make or to undo our mistake if we would have already passed a higher amount of flow through a particular pipe. So let me again restate it. Residual graph is a graph which would help us to undo a mistake. So this is the initialization step, right? We initialized a particular flow through all the pipe. Now, I don't know what is the maximum flow, but there would be but let's say in the maximum flow, whatever passes through this 12 FE pipeline, right? FE pipeline, let's say I don't know what would be passed, what is the amount that would be passed through the FE pipeline when the flow is maximum. When I have reached the maximum flow, at that point of time, what is the flow from the FE pipe? I don't know what amount would it be. But it might be 8, it might be lesser than 8 also. Right? Assuming that 15 plus 4, 19 is not the max flow, assuming it is not the max flow, you might see that when 19 is the flow, when my flow is 19, here the flow is 19, right? Okay, so this is what I'm trying to say. If now the flow is 19, assume the maximum flow is more than 19. Okay, we have not yet reached what is the maximum flow, but assume it is more than 19. The point I'm trying to say is, when we reach the maximum flow, the flow over here, right, or the flow over, let's say, in any one of the other edges, let's for example take this edge and state the flow in this edge when the max flow happens might be lesser than 8 also. Okay, so don't think that in 19 flow it is 8, and therefore if the maximum flow is, let's say, 20, this should be more than 8. Or let's say if it is 24 or 20, not 25, because the max flow can be 24. So let's say if the max flow is 24, so when we reach the max flow, the amount of flow which is passing through FE should be more than 8. I am stating it might be more than 8, but it can be 8. What's more intriguing factor is it can be lesser than 8 also. Okay, when the max flow happens, the flow got increased, but this can get decreased.
Did not get, sir, actually.
What is now? What is the current flow now? Flow means
Current flow 19.
19 is the current flow, because that 19 amount is coming into the sink, right?
Correct.
What is the flow through the FE pipe?
8.
8 is the current flow. Now, if I tell you that the maximum flow is 22, suppose. Okay, now we have reached 19, but the maximum possible flow through this network that can go into the sink and come out of the source is 22, suppose. Okay.
Yeah.
Now if I tell you when we reach the maximum flow, then these values would be different. I mean, because some other extra amount is coming. Now 19 is there.
Yeah.
Right?
Yeah.
Now
Yeah.
I am telling you, when we reach the maximum flow equal to 22, this value through the pipeline FE can be less than 8. That's what I'm saying.
Yeah, can be, because anyway, we are just fixing 20 22 or like that, more than
Yeah,
that. Then
but
it can be less also, more also, equal also.
more and equal, think a little bit deeply. More and equal is still very intuitive, that you can keep 8, that is fine, or you can pass more, because anyway my flow would increase. Therefore, the flow through FE pipe will also increase. That is more
Yeah.
intuitive. But if you try to think the flow through FE pipe is decreasing when the overall flow is increasing, it is a little bit counterintuitive. It is as if that there is a pipeline. Think in real life term. Forget about algorithm PDSA. Think in real life term, you have a pipeline setup, and the output of the pipeline setup got increased, but in one of the pipe you are passing actually lesser flow at some point, right? Initially the output was less, the overall output was less, but your pipelines were at a higher pressure. That is, more water was passing through one of the pipeline. But
Hmm.
after some point your output got increased, the final output got increased, but at that point one or two pipeline is actually having lesser pressure, is actually passing lesser amount of water. This is
It
counterintuitive.
means it means other pipelines have increased their
that,
pressure,
that
no?
that is obviously the case. That's what I'm trying to say. Keep this thing in mind. It might be the case that every time, that is the reason that greedy algorithm would not work. If you increase the capacity of all the pipeline, then you might not, I mean, it would not follow the conservation, and at some point you would get stuck. It wouldn't be the maximum flow. The very important point to notice over here is it can be the situation when the max flow, I mean, when the flow is getting increased, of the final flow is getting increased, some pipes, the flow in some pipes may decrease and flow in some other pipes may increase. Fine. This is a very important point. So now,
Hmm.
how will we understand flow through which pipe should be increased and flow through which pipe should be decreased to reach a maximum flow?
This
That's
is the question.
This is the question, and the answer to that question is residual graph. Is the context clear? Why residual graph is needed? Right? That's the point. Because it's not always the idea that I'm trying to increase the flow through all the pipe, and that would lead me to a max flow. It is not correct idea. We can think that okay, I would always try to increase the flow through all the pipe, and at the end of the day I would have a max flow. Max flow means then I can ensure that maximum amount of water is coming into the sink. That is not a correct approach, right? We might have to increase flow through some pipe, and we also might have to decrease flow through some other pipe. Now, to answer that question, from where to increase and from where to decrease, we draw the residual graph. Okay.
So what do you mean by the residual graph exactly?
That I'm drawing. But before coming
Okay.
to that, the context should be clear. Why it is needed. Okay.
Mm-hmm.
Fine. So now, what is the residual graph? Let's draw it. Residual graph, the definition is as it says, it is a residue. That is how much amount is left over in each pipeline. So if I draw the residual graph over here, A, so how much flow I have passed from A to F? 16, right? So when you have passed 16 from A to F, that means what is the residue in A to F? That how much amount of water I can pass more into A to F? Nothing, because it is saturated. I cannot pass anything else. It is 16 out of 16 is taken. So whatever is the amount of flow that you have already passed into in this graph, right? In G, let us call it as G and let us call it as R of G, residual graph of G. So whatever is the edge, 16, right? AF is the edge which is passing 16. You draw the opposite direction edge, because you cannot pass 16. You can pass 16 from F to A. That is, I can reverse. I can reduce the amount 16 from F to A, but I cannot pass anything more from A to F. So A to F would be 0. A to F would be 0. Okay. So I cannot pass anything else from A to F. So it is 0. But I can pass whatever is passed already. That is, I have passed already 16 from A to F. Therefore, I can reverse that. I can reverse that. So therefore, I can residue it from F to A. Okay. So since this is 0, I would delete this edge. It doesn't make any sense. Delete that. And I would draw this edge, F to A. So what is, I have already passed from F to E, 8, right? So 8 is passed from F to E. So I can reverse it by E to F 8. And what is the residue? 4 is the residue. Why? 12 minus 8 is 4. So 4 I can pass, 4 more amount of water I can pass from F to E. That is the residue, right? This is the direction. So I can pass 4 more amount of water from F to E, and I can reduce 8 amount of water which has already been passed to E in this G graph, right? To F, right? So therefore 8 is the opposite and 4 is the front direction arrow. So basically what I am doing in each of these step is, whatever is the amount of water that I have passed from, let's say, this F to E or all the edges, I would draw an opposite edge to that amount of water. So here it is 8 F to E, so opposite of E to F is 8. Here it was 16 A to F, so opposite of 16 F to A, right? And the residual amount which is there, that I would draw in the same direction. So F to E, 12 minus 8, 4 is there. So 4 I would draw F to E. So 4 is drawn F to E. And 8 was already passed, so A I would draw E to F. So 8 I would draw E to F. Okay. Likewise, this is what the residual graph is. So we would draw this. Here I passed 10, it is saturated. So since it is saturated, I would pass in the direction from F to B. I have already passed 10, right? So since I have already passed 10, I cannot pass anything else, but I can return the 10 that I have already passed. So it is opposite direction 10. Now here I have passed 2 in the, from B to F I have passed 2, right? So B to F I have passed 2. So residual is what? 4 minus 2 is 2. So I can pass more amount 2 from B to F, or I can return the 2 which I have already passed. Okay. Okay, fine. So here it is 13. So either I can pass more, how much? 10, right? 13 minus 3 is 10. So in this direction, I can increase by 10, or I can decrease by whatever I have already passed, which is 3. Likewise, now you fill up. This would be 9 because I have not passed anything. So I can pass 9 more. This is I have passed 7. So I cannot pass anything else, but I can return 7. This is I have passed 15, so I cannot, so I can pass, I can return this 15, or I can increase the flow by 5 more. And here I have passed 4 out of 4, so basically I don't have anything. 0, it would be.
From D to C, 4.
Yeah. Here it is 11
D
and
to
14.
E. Yeah, 11 and 13, 3.
So now this is your residual graph. Okay. Now, so draw the residual graph. So step 2 done. This is our residual graph. Now what is step 3? Step 3 is find the augmenting path in residual graph RG. So what is an augmenting path? Let's take blue. Or let's take green color. So now we would see what is an augmenting path. See, Augmenting path is same. A is our source, but augmenting path is a path from the source to the sink in the residual graph. Okay. So from A to D, I would travel, right, from A to D. Find me a path from A to D so that it reaches from A to D. Right? So how can you do that? There can be multiple paths again. So yeah, you can pick any one of them and solve it accordingly. I mean, it would proceed only again. Yeah, only
A,
the
B, F,
yeah,
A, B, F,
just a
E,
minute,
C.
just a minute. So only difference is that if you have, let's say, 4 or 5 possible path, okay, you choose a particular path, any one of the path you choose and proceed with the algorithm, it would work. Okay, it doesn't matter which path you choose. Only difference is, again, it might increase or decrease the number of iteration that you have to go through. Without, I mean, only that is the difference. Here, whatever you initialize, here, whatever path you choose, it wouldn't make a difference to your answer. Only thing is the number of times you have to repeat that might increase depending upon which path you are choosing. That's it. But answer would converge to the same thing. Now, how I would prefer to find a path, right? In the exam hall, you have to solve this. So basically, you have to be a little bit quick about it. So how can you do is, don't start from A, start from the end and try to see that in order to reach D, what are the possible options that I have. Now you can see that here I have an opposite arrow. If I'm coming from A, I can never reach D using this one or this one, right? So only option is to follow this particular edge. So I can have this edge, therefore it is coming to E. Now I have to see that what edges are that I can take to reach E. That's our point. So
F, E only.
F is the only possible option. Okay, great. And then if it is the scenario, then I have to reach F from A. So I can see that I can reach F from A by following either of these two, which is BF, BF, both basically 10 and 2. So I can take this one.
10.
Yeah. So let's take the 10 path, B, this FB, and then let's say this one, AB.
10.
10. So what is my path? My path is if I
And is it beneficial to take because the maximum capacity is required, so take the highest value?
yeah,
Is it?
exactly. Yeah.
Okay.
This.
4, 15. 4, 5.
Right. So this is the path that we have taken. This is our augmenting path. The green colored thing is our augmenting path.
But only 5 is coming here. Oh. No, right. 10.
ABFD. Now see. So augmenting path is found. Now step 4.
No, here 10 is the source, started from the source, but it reached only 5.
Sorry, what?
10, the value 10, A to B is 10.
Yeah.
Started with 10, but reached only 5. So where it was stored.
Now, in residual graph, you don't have to think about what is stored or not. It's just a graph. Okay, you only have to find the augmenting path and follow step 4 that I would now discuss. Okay. It's not a actual flow graph. Flow graph is this one.
Okay.
G.
It is intermediate condition in between, right?
Yeah. It is an intermediate step that
actually this is not actual. This is a virtual thing to solve the problem. Is it so, no? Right.
Yeah.
Okay.
This is an intermediate step that we are doing to backtrack our initialization. That's why I told what is the need of residual graph. The need is if we have already passed a greater value in the original graph through a pipeline where we should have passed lesser value, because we just understood that while we go to max flow, some pipes may have lesser value, other will have more value. Now, what if we have already done more value in the initialization? Then we must have a way to recognize that and decrease the flow through that pipe, right? So that is ensured by the residual graph. When we draw the residual graph, it is a backtracking step if we have made a wrong decision. Now, how to decide if we have made a wrong decision, that now step 4 would tell how to decide that.
Okay.
Right? So now we have found the augmenting path in RG, which is A, B, F, E, D, whatever. Now, once you have found the augmenting path, the next thing that you have to do is find the bottleneck capacity in the augmenting path. What do you mean by the bottleneck capacity? The least capacity. So here 10 is in the, let's say in this augmenting path that we have now, What is the minimum value of the weight that in this path? So 10, 10, 4 and 5. So we can see 4 is the minimum possible capacity, right? In this
Yeah.
10, 10, 4 and
Yeah.
4.
Yeah. Yeah.
So bottleneck capacity is 4. So find the bottleneck capacity is your next part. Now this is the most important thing. After you find the bottleneck capacity, for every edge in G, or not along, fine. So this is what we have to do. That for every edge in G, once you have found the bottleneck capacity, which is 4, for every edge in G on the augmenting path, right? So we have A, B, B to F, then F to E and E to D. This was our path. So we would say, we would actually follow the same track in
G.
G as
What we are carrying? G is the original one graph.
G is this one. RG is this one,
Okay. Yeah.
right?
Okay. Sorry.
So what we would do is in every edge on G, just bear with it. See once I complete it. So when you are in G, we would go through the same trajectory or same along the same path that we have found in the I mean in the residual graph, the augmenting path. So this is the augmenting path, right? We call it the augmenting path. This green color. We would travel exactly these vertices in this order in the G graph, and if I see that that particular path edge is in the same direction as in the residual graph, I would add the bottleneck capacity with the current flow. I know once I complete it, it would be more understandable, but let's just bear with it. So I would add the bottleneck capacity to the current flow in my original graph. If it is a oppositely directed edge than the residual, than the augmenting path, then I would subtract the capacity. So let's now take the example and it would make more sense now. What I'm saying is bottleneck capacity is 4. Now let's see what was our augmenting path. Augmenting path was A to B, right? This green color A to B. Come to the original graph G. Now you see what is the direction of the edge from A to B. I mean not from A to B, between A and B. So I can see the direction is A to B, right? It's flowing from A to B is the path, and through this path, A to B is the edge, and through this edge I have passed 3 value. Here also the augmenting path was in green color and it is also directed from A to B, right? So here also A to B, original graph also A to B with a value of 3, right? So since it is in the same direction, augmenting path and original graph edge, therefore I would add the bottleneck capacity. Mr. Srikanth, can you mute please? Again, background noise is coming. Yeah, thank you. So I would add the bottleneck capacity. Fine. Now let's take the next thing, which is this particular path, which is B to F. Now let us see what is the direction of the edges from B to F. Let us see. In our original graph, B to F, I have passed in this direction. B to F is there, right? So in this way. But the thing is, here another path is there, F2B, right? F2B 10 was there. Here, which one I have considered? Please be careful in this kind of scenario. Which one I have considered? I have considered this 10 one, right? This 10 capacity one. Okay. So in this 10 capacity one, this was green colored. So, and so that means which is basically this path we are considering, this edge we are considering, which was 10. Now you see, what was the direction of the edge in our residual graph? It was from B to F. But what is the direction of the edge in this particular graph? It is from F to B.
Yeah,
So that-
opposite.
Opposite direction, right? So what I have to do is I have to reduce the flow.
Hmm.
I have to reduce the flow. So this is an example. In this particular edge, I have to reduce the flow. So let's do that. How much? Again, by bottleneck capacity. Everything is happening in
4.
bottleneck capacity. So this would become 10 minus 4. Okay,
Hmm.
fine.
Correct.
Let's proceed further. 7, right?
4.
6 is coming. 6, 7, 13, 11, 12, 13. Okay, fine. So now let's proceed. Again, what was the next path? This 4, right? F2E. And here also I see F2 is the same thing. No problem over here. F2 is also going. Same
We will
direction.
add
So we will add 8 plus 4.
plus 4.
Right? Okay. This is done. Now what is the next step? E to D. E to D is 5. And is it the same direction? Again, same direction.
Yeah,
So
plus 5.
plus 4.
Plus 4, yeah, sorry.
Bottleneck capacity. So now let us write the value and see what is happening. 8 plus 4 is 12. And this is what? 10 minus 4 is 6.
Don't delete, sir. Don't delete, sir. Sir, write in the another color so that we can.
Okay, fine. Let's
Another,
keep.
we will compare it now how it is.
So this was
10.
what? 8 plus 4, right?
8 plus 4, sir. Yeah.
Let's keep it like that only. Okay.
Yeah, different color. Yeah.
Let's take this color. I don't know which one to take. Okay.
Any color. More colors, more confusion.
Yeah. So this is 12. I don't feel it's making any. Let's take green only.
Yeah, green only.
8 plus 4 is 12. This
12,
is
12.
6. This is 7.
Yeah, 7.
This is 19.
19.
Fine. Now let us just check that whether all the flows are correct or not. So here I am passing 16, right? Here I am passing 7. Okay. Here 6 is coming. So 10 went out at this side. Okay. Okay. Let me just check the final one. 16 plus 7, right? 16 plus 7 is how much?
Final was in okay. 19 or 23.
23, right? So then it is correct. 16 plus 7 is also 23. And here it is 19 plus 4 is 23. Then fine. And your capacity constant is followed at all the places. So therefore, you don't have to check anything else. Just check the input and output summation. If that is equal and you have followed the capacity constant, then it is bound to be correct. So anyways, you can check, it would be correct.
Yeah. Still, let us check it once.
Okay, fine. Check.
Correct.
So, but for your examination point of view, I'm telling, don't go into checking. Just check the summation. Okay. So 7 is coming at this point. Okay. And then what you are doing is 6 is coming from top. So 6 plus 7 is 13. You are getting at B. So 2 you are moving at the top. So 11 is left. 11 you are passing here. Okay, done.
Correct.
16
And
is
2.
coming here. 6 has already gone out. So 10 is left. 2 is getting added. So 10 plus 2 is 12.
Yeah, correct.
12 came over here. And after that, from here 11, you're passing 7 on the top. So 7 plus 12 is 19. So 19. 12 came from here and 7 came from here. So at E, I have 12 plus 7, which is 19, which is 19 over here. And here I came 11 and gave 7. So 4 was left. So 4 is getting passed. Correct? No problem. So yeah, but again, repeating from your examination point of view, check the input summation and output summation. That's it, and check the capacity constant. If every flow is lesser than or equal to the capacity or not. If these two conditions are holding, then you don't have to check individually at all the point.
Okay.
Right. Okay. So you see that now we have satisfied all this. I mean, this is thing. And what were the steps that we followed? We draw the residual graph. We take any random path in the residual graph from the source to sink. We follow along that path and we would consider the corresponding edges in the original graph. If the edges in the same direction, see A to B was 3 and A to B here also I was the same direction. But here I was taking B to F, this 10 one, right? B to F, but this 10 is in opposite direction in F to B. I followed this particular edge. It was in opposite direction. So therefore I would reduce the bottleneck capacity. Wherever it is in the same direction, add the bottleneck capacity 4. Why bottleneck capacity? Because in the augmenting path, the minimum capacity is 4. Right? That's why that is the bottleneck capacity. This is your bottleneck. Okay. So bottleneck capacity is 4. So add the bottleneck capacity along the same direction edges and subtract the bottleneck capacity if the is same, else subtract the bottleneck capacity in G. If it is in opposite direction, subtract. So here it is from F to B is 10. Here it is B to F is 10. So that means I have to reduce the bottleneck capacity. So in the opposite. So reduce 10 minus 4 is 6. Here F to E, here also I got F to E. This green path is from F to E. So same direction, so add bottleneck capacity, which is 4. Right? So 8 plus 4. And then finally E to D is also in this green path and E to D is again same. So 15 plus 4, 90. So now we got this flow. Okay. Now, is it the maximum flow or not? We don't know yet. So again, we have to draw the step. The algorithm is over. Once you do this new initialization, you got a new initialization, right? Initially you had 8 over here. Now you got 12. So with this new initialization now, again I have to draw the residual graph. Okay. New residual graph. So I would delete this residual graph and we would draw another residual graph. Or
Sir, why bottleneck is working here?
that's a good question. But let's finish this algorithm and then we would answer those doubts. Why bottleneck
Now,
is
what?
Okay.
But in this step, what we get in this
we,
residual graph?
we get a
What
new
actually?
we get a new initialization of the flow network. So initially
Okay.
8 was here, right? So now I got 12. So see what are the changes? Now I would delete the values. Okay. Initially I had 8 over here. Now I added 8 plus 4 and I got 12 over here. Initially I had 10 over here. Now I subtracted 10 minus 4 and got 6 over here. How can you make this decision that I should subtract from a particular edge? Which edge I should subtract and which edge I should add? I don't know that. In order to
No,
maximize the flow.
this is okay. This is okay. First we initialize randomly, and then we got the residual graph, and we get the another initialization. But we can get a number of initialization this way, no?
Only thing is that if you take random initialization, there is no guarantee you are going towards the maximum flow. You can go away from it also. But if you follow the residual graph technique, you are always converging towards the correct maximum flow value.
Okay. Because bottleneck is being used, so this bottleneck will be added every time, right?
Yeah. Okay. And the reason for that is a little bit more beautiful or intriguing, and I would discuss that. Why now? At first, follow the algorithm. Once you know the algorithm by heart, then we would try to go into the intuition of why the algorithm is working. So I would tell then why it
That
is
is required. Why it is correctness?
why it's
Correctness check.
yeah. So that I would come to later. But at first,
Okay.
let's complete it. Okay.
Fine, sir.
So
Got it.
yeah. So the step is draw the residual, have a random initialization, draw a residual graph, find an augmenting path, go along all the edges in the original graph along the same augmenting path. If you find that the edge in the original graph is in the same direction as in the augmenting path, add the bottleneck capacity. If the edge in the original graph is in opposite direction to the edge in the augmenting graph, then subtract the bottleneck capacity. And therefore, you get a new flow, new initialization of the original graph. Once you get a new initialization of the augmenting graph, then again, you draw the second residual graph, state 2 residual graph. So this is your iteration 2. So it's iteration 2 residual graph. So I would now draw the iteration 2 residual graph and let's do it in another place only. I would delete this top one. Okay. Step 1, step 2. Fine. So next residual graph. Fine. Again, let's follow the same rules of residual graph. We draw opposite direction edge, right? So this is 16. Then what? This is your 7, right? So this is opposite is 7. In this direction, I have 7 minus 30, so 336. Again, this is 4. In this direction, I have passed 6. Again, for 2 and 4, I have 2 can be passed in the opposite direction, right? And 2 can be passed in the same direction as well. Fine. For this, I have saturated the place 12, so 12 can be returned back. Okay, this is 9. 11, I have passed in this direction, so the 3 I can take back, or I can return 11 over here. This is saturated, so it would be opposite 7, right? And it is 19, so I can either return the 19 or I can add 1. And this is also saturated. Fine. So this is my residual graph 2. Residual graph 2. This is my residual graph 1. Okay, so same steps. Once we have drawn the residual graph, step 2 is find an augmenting path. So tell me an augmenting path from source to sink, A to D.
Go from backside, na?
Yeah, tell me.
19, D to E, E
Okay.
to F, F
Now,
to A,
wait, D to E, then
E to F, and F to B, and B to
now keep this thing in mind. We are going from backside, but we have to reach from A to D. So here, what was the technique? D to
A,
E.
B, A, B, F, E, D. A, B, F, E, D.
Sure about that?
A, B, F.
How can you go from F to E?
No, no, no.
The direction is
we
opposite.
can't.
It is from E to
Yeah,
F. It's not from F to E.
Hmm.
It's visible,
9 we
right?
can use. We can use 9 also, because
Wait. Let me make it big. Wait.
no. What about the 9? 9 we have not used at all.
Fine.
And
You
then
can use anything. Whatever edge is there, you can use any edge. Just tell me a path from
okay.
A to D.
A, B, C, A, B.
Don't take it that way. Always start from the back. But keep in mind that you are starting from back, but you have to reach from A. That means you have to think the edges in the other direction. So in this, how did we do it? In this example, come back to this example. How did we do that? I have to reach from A to D. Okay. So D,
Yeah.
So come back from this edge, but see the direction
E.
is from E to D, right?
Got it, got it, got it. D, E,
DE,
F, B.
then you have to reach E somehow from A. So see all the edges
Yeah,
that is coming into E, not out of the E. Do not consider this edge. So into E
yeah.
is this edge. That's why F to E. Right. So now
Only incoming edges we have to consider, right?
exactly. Now apply the same concept in this graph. I have to reach
So
D. Okay.
D to E is okay. D to E,
After that,
but there is no
After that,
incoming edge to E.
yeah, there is no possibility.
there is no
So
possibility. That means you have.
okay,
That means it's at converged. It's done. Your answer is come. Max flow is 23. Okay. So
okay,
since
okay,
so
okay, okay.
once you have no other option to somehow, what is the residual graph doing? I told you residual graph is an intermediate tool or a intermediate virtual step which we are making to backtrack our mistake. If in the initialization phase, I have increased the flow in a particular pipe, but in the max flow position, that pipe should have lesser flow and some other pipe should have more flow, right? If this is our case, then how to understand in which pipe I must reduce and which pipe I must increase? So in order to take that decision, I must have a data structure or I must have an intermediate step where I can undo my changes, right? Whatever change I did in the initialization phase, I must be able to undo that. Now, what is happening in the residual graph is I am drawing an edge, right? Now, see, now this would make more sense. In the residual graph, what did we do? We drew an edge equal to the flow in the opposite direction. So let's say in the original graph, I have a 16 flow in this direction, right? A to F flow is 16. In the residual graph, I drew a flow in the opposite direction of 16. F to A is 16 now. In the original graph, I had a flow initially 8 from F to E, 8. In the residual graph, I drew an edge in the opposite direction, E to F, 8. And the residual capacity 4 is from F to E. So what does this 8 and what does this 16 in the opposite direction signify? They signify our backtracking. If I use this edge or this edge in my step of finding the augmenting path, that means I am actually trying to reduce the flow. I am reverting my decision that I initially passed 16 in this edge, but it seems that in the original case, I have to reduce the flow. So in this example, in our example, only take this. I have passed initially 10 over here, right? 10 was the initial flow. So from F to B,
Yeah.
I was passing 10. But I saw
Hmm.
that in the augmenting path, B to F is 10. So what does that mean? That means although I am passing liquid from F to B, but in the max flow situation, F to B must have lesser flow because it is a part of the augmenting path. And that's why it is in the opposite direction. Okay, so that signifies that I must reduce the flow in from F to B. It should not be from F to B, it should be lesser by the bottleneck capacity. Okay, so therefore this is undoing. We were only able to find this B to F because B to F is the undo step of F to B. F to B 10, F to B 10, undo is what? B to F 10. So that's the edge. See, B to F 10 is the edge in our augmenting path. So every flow that we pass through in the real graph, we write an undo step corresponding to that particular flow in the residual graph. What is the undo step? Undo step is whatever capacity you are passing in the original graph, reverse the direction of the edge to undo the effect of that and keep the capacity whatever you are passing. And you have an option of passing the leftover capacity in the same direction. That I might either reduce it or I might either increase it, right? So let's take this particular path. Here initially I was passing 8. 8 was passed from F to E. But again, here I chose 4 as the F to E, 4 was chosen. So what does that mean? That means this is in the same direction F to E. Here also it is in the same direction F to E. That means whatever was the initial flow, that is fine, but you must add more, right? Because it is in the same direction. That's why I'm adding. And B to F is in the opposite direction. That's why I'm subtracting. Okay. So the residual graph is basically the undo step for each of the flow that we have in the original graph. And the augmenting path is basically a path which tells us whether I have to undo at a particular pipeline or whether I have to increase the flow at that particular pipeline. That's the whole concept. Now, once you draw it, you get a new initialization. With that new initialization, you draw another graph, residual graph. in that residual graph, if you are not able to find any augmenting path from the start to the end vertex, that means your algorithm has converged. That means you cannot further increase the flow because you don't have any augmenting path left. So that means whatever flow we have now, which is basically 19 and 4, right? 19 and 4. So your flow is 23. Then this flow is the max flow. Why it is the max flow? Because there is no augmenting path in the residual graph. That's the proof. That's the guarantee. You cannot have a flow more than this. So through this network, 23 is the maximum possible flow. And we told initially that since the summation of the capacity of the two edges which is coming into sync is 24, that's why our maximum flow must be lesser than equal to 24. Right? We told that. So since we told that, we saw now that the max flow is actually equal to 23. So that means this network could have supported 24 flow, at least looking till this point. Look, sorry. Oh, Control Z doesn't work. Right. So this is 19, right? Yeah. So looking,
19.
Looking at least till this much amount of the area, right? We can say that the maximum flow could have gone till 24. But it is not actually possible. Why? Because the internal structure of the network is such that you cannot have a flow of 24.
Okay, we cannot achieve 24.
You cannot
right?
achieve 24. Exactly. It is lesser than 24. Actually, it is equal to 23. Therefore,
Whenever the residual graph will, the backtracking will fail, we will leave that graph. Okay, previous one will take. Okay.
Yeah, whatever initialization you have, right? So you drew this residual graph from this original graph, right? You have this. Let me delete all of this and now put the initialization since you all have already understood. 12 out of 12.
Yeah, I got it. No problem.
No, I would have to discuss 7.
Actually, RG1, RG2, we did, right?
Yeah.
RG2 is the final residual graph, right?
Yeah.
And RG3 failed. RG backtracking in the RG3, it failed, right, no, sir?
Yeah. Not RG3. RG2 only failed. This was the first residual graph.
Okay, yeah, RG2 failed. G, RG1 and RG2. RG2 failed, so RG1, got it. RG1 is the final one.
RG1 is the residual graph. The original graph is the final one for which you drew the residual graph. See, residual graph G2, you draw that on the basis of the new flow graph that we had. This graph, right? Here you did 8 plus 4. Here you did 10 minus 6, 10 minus 4. So after doing 10 minus 4, you got 6. After doing 8 plus 4, you got 12. So
okay. We are making changes in the original graph based on the residual graph, right?
Yeah, that's what I did, na? So that's what I did.
Sorry, got it.
Yeah. So once you have this graph, and then from this graph you draw the residual graph, right? For the new initialization. And when in this residual graph you are failing, that means that graph for which you drew the residual graph, that is your final state. So I drew this residual graph in which I could not backtrack. This residual graph was drawn from this graph, right? From this graph. Therefore, this is the final answer. Okay. Okay. So therefore, the max flow is 23 and we cannot have anything more than that on this graph. So answer is 23 is the max flow.
Suppose we could have started from A16. We started from 16 and 7. We started from 1 and 1. Then a number of iterations will increase, but the final result will come the same, 23.
Exactly.
Okay. So let us make practice on this. Our practice will be also there. Okay. Got it.
Yeah. So you can, but don't start from 1 and 1. It would take a lot of time. So
okay, let us take a lot of time, so confidence will be more. Okay.
So you have to do that on your own because that would take. I have to cover all.
No, sir, not here. No.
Yeah.
We will do. That's. I ask whether we should do or not. Okay.
Yeah.
I will do.
Yeah.
I will make a practice of that.
Yeah. So just check that out, and it would take many iterations, but the steps are same. Have a
Okay,
random initialization, draw residual graph, find augmenting path, find bottleneck capacity, follow along that path in the original graph. If the edge is in the same direction, add bottleneck capacity. If the edge is in the opposite direction, subtract bottleneck capacity. You get a new initialization in the original graph. For this new original graph, again draw the next residual graph. If there is no path that you can find in the residual graph, your algorithm is terminated, and the original graph for which you drew the new residual graph in which you couldn't backtrack, that original graph is your max flow graph. I mean, whatever flow is
great,
there,
great, great, sir.
right? So that's the whole concept.
The
So
whole algorithm you have just
yeah, so that was a summary of the whole thing.
right.
So yeah, so this is our Ford-Fulkerson algorithm. Now the thing is, another new concept for that, which is the cut, right? Now this is super beautiful. I mean, this is so elegant. So this is one type of question that might come, that is what is the max flow. And now we would address the next kind of question, which is the minimum cut. Now what do we mean by a cut?
Cut, yeah.
In fact, this is I mean, I like this particular thing much more than the first one. See, what happens here is,
Minimum cut is dangerous thing, sir.
no, it's nothing dangerous. Actually, you have already found the minimum cut.
No,
You
no,
just don't know it.
no,
Yeah.
sorry. In this, not in the mathematics here only. Minimum cut in the business is dangerous.
Okay. Yeah.
Sorry.
Fine. So what is a cut, by the way?
Cut. Cut.
Cut is basically a partition in a flow graph. Okay. By the way, one more thing I would try to tell it now, that whatever definition or this kind of thing that I write, the textual part, right? I write it from my own on my, I mean, so what I'm trying to say is, if you are writing in some subjective exams, right, where you have to in your colleges or somewhere else, if you're writing in some subjective exam, I would request all of you to follow the definition in the books if you are writing a subjective exam. Okay, whatever I'm writing, yeah, whatever I'm writing, that's on running. I might miss a point. I mean, formally, I might miss a point. What I'm writing just to discuss the concept. Okay, so don't just so yeah, don't do that. So a partition of vertices in a flow graph such that it separates or disconnects. So this is basically a definition of a cut. So which you're cutting it. You're cutting the graph in such a manner at some point in between, right? So that the graph is being partitioned into two different sets. And one set would be having the source vertex. The other set would be having the destination vertex. So this is a cut. So let's say I have, right, these two sets. This is basically a cut. And I would put, let's say, the source A over here and the destination D over here. Now I can have any vertex in these two sets as long as they are separating out the path to reach from A to D. So let's say I have A, F, and let's say B. Okay, and let's have AFB I have taken as one particular set, and let's say DEC is the another set. So this whole thing is a cut. I'm just saying that, let's say this whole thing is a cut. So DEC and AFB, these are two different set. So if you have to make a cut, all you have to do is just take two sets, put source vertex in one, put destination in the other, and then whatever is left you can arbitrarily assign. I mean, it should make a sense that you are separating the part. If I put E over here and let's say, sorry, if I put F over here and E over there, right? Something like that, then it would be difficult, because with D I have F, with D I have F. So I cannot, and A I have E. So I cannot separate it in this random manner. I have to keep up way so that I mean the source and the vertices that I'm considering, they are together in one side. Like here I have this A, F, B together in this, like over here.
Connectivity should be there.
Connect, yeah. So I have to do it in such a manner, so that after the partitions I make, they should disconnect the source and sink. That should be kept in mind. Okay, if it is not disconnecting the source and sink, then it's not a cut. Like if I am writing AFB and DEC, so this is AFB, right? So this part AFB is a part, this is a set, and DEC is another part, right? And that means I can basically say I'm segregating at this point. In the middle, I'm cutting it out. So if I'm cutting it out in the middle, so that's basically, I mean, that's a cut, because I'm doing that. I'm separating out in these two subparts. Or I can, let's take another example of a cut.
Can we take AFEB and CD only? One side 4 and one side 2 only?
Just a second. Let me
Okay.
delete it. Fine. Yeah, what were you telling?
AFEB.
AFED. D must be separate.
No. AFEB.
Yeah,
B for
correct.
Bombay.
Exactly, yeah.
And only 2 in the another side. We can take it.
Yeah, fine.
Okay. It disconnects, right?
So this is one, and let's say this is one.
Second one is CD only, right?
Right. So what is the line in between that I can consider now? Then this is the line.
Means 2 disconnected graphs we have to choose, right?
Exactly. I have to separate into 2 parts. This is also fine. Now, if I say that I'm taking A, E, and C, and D, F, and B, so how can I draw this color, right?
No.
Right? Then it's
Not possible. Not possible.
Yeah.
Like two connected graphs separated by a partition, right? No?
Partition, exactly. Yeah.
Got it.
Right, and the most important part is source should be one and destination. That's from that point we are actually saying it is segregating. That's the disconnect.
In one set, one source should be there, and in the second sink should be there.
Yeah, exactly.
Yeah.
Fine. So that is the definition of a cut. Now we are saying one important fact, right? So tell me this thing. Now we would just talk. We would not do any algorithm. Now we have to just follow a little bit. Intuitively, you have to follow some things. Suppose I take a knife, okay, or let's a cutter, a big cutter, mechanical cutter I have, and at this point, let's say, what should I do? Let's say at this point, I cut it out. Okay, I take a mechanical cutter, fine, and I cut it out, cut this part out. Fine. Now, how much water? So just assume this is a real pipeline structure. And with the mechanical cutter in this red line, I have cut all the pipes. So this pipe got cut, right? This one got cut, this one got cut. These 2 lines got cut, this line got cut, and this line also got cut. So all these lines of pipelines got cut, right? So how much water will come out from these cut pipelines, right? You have cut the pipelines in between. So can we tell the amount of water that would come out in this state? Just we have reached the max flow state.
From each pipeline you need, or
no, from overall. So from overall means from this whole thing. I mean, consider this sky colored portion I take and put it in a bucket. So what would be the amount of water inside that bucket? The total output from this cut part, right?
22.
How it is 22?
Sir, what is the sink for that cut part?
There is no sink now. The cut does not have a sink, right? Cut is basically you have cut out the
Got it.
part of the network. So the
Yeah.
sky colored part, I have just cut it out. So that means from here water would leak, 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 from here water would leak. All this point water would leak out, right? I have cut it and separated it out, right? So A is the source, so all this water would leak from here. So my question is, how much water would come out?
No, 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 no. It is 7 and 4. 20. It is 20.
Is 20? Sure about that?
16 from A to F, it will leak. And 7. No, no, no. 2 will come 16 and 2, 18. And 4, 18, 22. 22. Confusing.
That's
Say
why.
many will also. No, no, 22 only.
So the water has to come from the cut part, right? Where the part
Only
was-
cut part only, na?
So there are
Yeah.
there are multiple cut parts here. So how much water will come?
The whole 16 will come from A to F, 2 will come from B to F, and the rest 5 will come from this. So 4 and 1, 5. No, no, right. The whole 5 and 23, 23. 23, sir.
23, sure?
Yeah, sure, 23.
Great, 23. So
23.
that's actually correct, 23.
I was confusing because here the whole water will come, na 16, the whole will be wasted.
Exactly.
When 7 will come, the 2 will go, and the rest 5 will go to the 11 to B to C, and out of this 5, 4 will go, and 1 will rest here.
West here, exactly. So it is 23, right? Correct, 23. It's therefore it is 23. Whatever now, let's do another exercise.
Beautiful, beautiful, really.
Let's
It
do
will always come 23.
That's the observation.
It is always come 23 because the flow is always 23, na? Because it is going, it will come out somewhere, whenever you cut, wherever you cut.
That
Yeah,
is
so
the,
it is totally based on input. If the input is 23, then 23.
that is
It cannot be stored. It cannot be stored, so it will come out. Very simple.
Yeah. So that is actually the observation. It would always be 23. Even if you can take this cut, take any cut the graph in any point, just follow the rules of cutting. That is, you put a source in one, put sink in the other. Once you do that and you follow all the conservation criteria, it is bound to be the flow which is coming into the network. Even you can take this cut that I just drew now, and you see that anyway it is still 23, right? So if I take over here, I mean, this is very easy. This example is anyway super easy because this is one output and this is one output. See, 12 plus 11.
No, what you did previously, no, it was difficult. It was the maximum cut. It was
Exactly.
you cut the whole
Correct.
partition.
So that was a bit difficult. This is easy. This is, you can directly see it is 12 plus 11.
Now because that, due to that, now it is clear. It is interesting.
Right? So the beautiful observation is it would be anyways, whatever you do, it is always the equal to the flow that is coming in, or let's say in this case 23. Now if that is the observation, if the flow through any cut is equal to the current flow in the network at that point of time, this observation, can we say this? Now see, this is the most beautiful statement. The maximum flow, or let's say not the maximum flow, let's break it down into two separate statements. Let's say statement 1, flow through any cut. Any is the most important term over here. Any cut is actually same and is equal to the flow of the network. Flow of the network means whatever initially was coming into the sink. That's the flow.
The flow of the network or the maximum flow of the network?
let's say even if we would not have reached the maximum flow, right? Not to, I am taking this example on the maximum flow, but let's say if we would not have reached maximum flow, just a random flow was already there. So like last
Oh,
time it was,
let us take this residual graph.
yeah, let's say in the previous case, this was not 23, this was 19. If you remember that we had 9, right?
Residual one, right?
Yeah, so yeah, residual one, we had 19 was the flow, right? So in that
Correct.
also, if you separate out the as a cut, right, then the in any cut it would be 19. Okay?
Yeah.
In
Of
any
course,
cut, output would be 19. So
Mm-hmm.
therefore, the statement one is flow through any cut or flow out of any cut, whatever language makes more sense to you. Flow out of or through any cut is actually same. Yeah.
Cut. Any cut means not a particular edge cut, no, the total.
Total cut means this definition, this cut, I mean.
Yeah. Got it.
Yeah. So in any cut, I mean, cut in the sense this cut, the definition of cut, not an edge cut.
Yeah. Got it.
Is actually same. This is very, very important. Any cut you do, any possible, keep source in one, keep destination in or sink in other, and take edges, take the vertices into two sets. Any possible random cut you choose, it would always be having the same flow out of the material or the water, right? That would be same for any cut. This any and same are the most important words over here. Flow out of or through any cut is actually same and is equal to the flow of the network, right? Flow of the network means, again I said, whatever the total flow, whichever is coming into the sink, when it was joined together actually. When you have not made the cut, whatever was coming into the sink, that was the flow of the network. Might not be max flow. This condition holds for any flow. By the way, this condition holds at any state of the graph, holds at any flow state of our network. You need not have to be in the max flow. Whatever is the flow, let's say the flow at a certain point is 12. Then you cut it into any possible cut, you would get 12 coming out of all the cuts that you have. Whatever is the flow at that point. Okay.
Sir, accordingly, we can suppose we cut, then we have A to B, but we left A of and F. If we left A and F, it will be 16, right? So we cannot do that. We have to cut. If I have to cut, then I have to cut the entire input source.
Yeah.
Because if I do that, then suppose A to F, there 16 flow is there, then it is still filling some sink, right? So it won't be 23 then.
No. You have to cut the whole thing. Otherwise, it's not happening, na?
Yeah. Okay. Yeah.
We have to fulfill the condition of
Condition.
cut.
Yeah.
Cut condition means that the two connected graphs should be separated by right.
Correct.
Two sets.
Correct.
Right.
Yeah. Okay. Fine. So flow out of or through any cut is actually same and is equal to the flow of the network. So this is my first statement, right? So you take the network, whatever is the flow in that network, observe that, and then cut the network by following the cut definition. You would take any possible cut you take, you would get the same flow, right? Now, why is this working? That's the question. Why it would happen? Why you can see that always this is happening? That any cut I am taking, it is equal to the flow of the network. Why it happens? It's very simple actually, and to observe. Why it is happening is because when I'm putting source into one thing, one of the set, right? And I am telling that there is no conservation or accumulation of your of water.
Yeah.
Right? If the water is not getting accumulated at any point, and if the source is in one set and the sink is in another set, so everything that is coming into the network, that is coming in from source, and everything that is coming inside the network must not be accumulated and must be thrown out. What I have done is just in the middle I have made a cut with a scissor or whatever, right? So that means whatever was coming into the network whatever set you cut you take, it must come out of the network because it is not getting accumulated in the network. If nothing is getting accumulated in the network, everything which was there in the network must come out. And what is everything which was there in the network? Whatever was coming in from the source, which was equal to the flow, right? Whatever was coming. So that's why
It is obvious. It is obvious actually.
yeah, it is obvious. That's the main point.
Yeah.
So,
Correct.
but the next thing that we would do is on this very obvious fact, we would get a very beautiful statement. Okay, so now if this is the case, if any cut I take, that cut is actually flowing, I mean, the net flow of the network passes through that cut. If I take any cut, right? If that is the case, I would use this definition to, to imply my max flow in the opposite direction. Now, what I mean is, fine, any cut is having the max flow at that point of time. Now, let's consider a state of the network when I have reached the maximum flow. Consider, okay? Now, any cut I take, right? Any cut I take that would pass the max flow through it, any cut, because that is the flow of the network at this point of time. If this is the situation, can I say that the maximum flow that I can have in a network is bounded by, or not only bounded, is decided by the minimum capacity cut in the network? Understand this?
Sorry. Once again, sir.
Yeah. Understand this. If so, let before coming to this definition, let us do one more little exercise. Now we would discuss one other thing. So let's say I make a cut at this point. Okay, I make a cut at this point. That AFB is my one set of vertices and ECD is one set of vertices, right? Now I ask you, what is the maximum possible capacity? Forget about, I'm not asking you max flow or what is the current flow, right? I'm not asking that. What I'm asking is, this is a new concept. This is not the one that we have discussed. This is not the flow. The flow would be equal to, the flow through any cut would be equal to the flow of the network. All those things are done. Okay, we just forget about all of this now. This is a new concept, and the new concept is the capacity of a cut. Till now, whatever we were discussing, that was the flow through the cut. Whatever was coming out of the cut, that is the flow through the cut. Now I am discussing a new concept, which is the capacity of the cut. Now, what do I mean by capacity of the cut? Okay, I would delete this because I have to now. This is a new concept, which is the capacity of the cut. Capacity of a cut. So what is the cut now? A, F, and B. And here it is E, C, and D. So this is my cut. Now what is the capacity of this cut? The capacity of this cut is basically what is the capacity of the outgoing edges between these two cuts. So let's say AFB is this cut. This is, let's say, not cut. This is set 1, this is set 2. Set 1 and set 2 is basically implying cut. So let's say set 1, this is set 2. Capacity of my cut, this set 1, set 2 cut, is the edges which is coming out from set 1 and moving into set 2. The capacity of these edges. So let's say this is E1, this is E2. So capacity of E1 plus capacity of E2 is equal to capacity of the cut
Into 2.
S1, S2. Equal to, so when till now we have learnt about capacity of an edge. So let's say this is the edge, ED is the edge, its capacity is 20 and 19 is the flow. So for an edge, the flow is 19, ED edge, 19 is flow, 20 is capacity. Now we have learned something called the cut. If I tell you what is the flow through the cut, that we have already seen. What is the flow through the cut? You did it on your own in all these examples. Now the next thing is, if I have now learned the flow through the cut, now just like edge we had flow and capacity. Likewise, cut has also flow, which we discussed over here, and now cut also has capacity. Now, what is the capacity of a cut? Okay, so this is the same cut that we are talking about. Now, what is the capacity? Flow through this cut is 23, right? We already know that flow through this cut is 23 at this point. Flow through any cut is 23. So, flow through this cut is 23. That's done. But what is the capacity through this cut? Capacity of this cut is, the definition is, you take those edges which is coming out from this S1 set and going into this S2 set and find their capacity and sum them up. So what are the edges? So AFB is this set 1 and ECD is set 2. So AFB is set 1. My question is, what are the edges that are coming out from this AFB boundary and going into the ECD boundary?
FE and BC.
FE and BC, right?
And
Correct.
26.
So 12 plus 14, 12 is the capacity of E1 and 14 is the capacity of E2. So capacity of the cut is 26.
26.
Fine. Let's do this for some couple more example to make ourselves clear with the concept. Let's take another cut. Let's take, this is also a cut.
Previous. Yeah.
And this is also a cut. So what would be the line? The line would be something like this.
Yeah.
Okay. Now what is the capacity of this cut?
13 plus 10 plus 12.
All the outgoing edges, right? So what are the outgoing edges? This is an outgoing edge. So from F it is going to E, right?
Yeah, 12.
So 12
F,
would,
E,
right? 12 would be
F,
considered.
E, F, E, FB and AB.
Yeah. So let me write it over here. FE.
35.
Yeah. So plus FB, whatever is coming out of the set AF, whatever is coming out of the set AF is basically my edges. So FE, AFB, and AB.
Correct.
Right. So then what is the summation then? Capacity of FE is what? 12.
12.
Capacity of
And
FE is
10.
10.
And 13.
AB is 13. Right. So this is how much? 20, 30, 35. Right. 35 is the capacity of AF. So now let's draw it. I mean, let's keep this thing in mind. This is what? AF, right? Okay. AF is 35. This is... So, number 1, what that is ABF was one set, ECT was another. The capacity for this cut was 12 plus 14, right? 12 plus 14 is 28, 26. Fine.
26.
The second cut was
AF.
and B, E, C, D,
P.
right? Which is 35.
35.
Okay. Let's take another. Let's take this one. Okay. So let's take this one. So that means what? That this is basically moving like that. So my cut would be something like this.
ABFC.
Right. So this is my cut. So all the outgoing edges for this is A, F, B, and C are together. ED is over here. So what is the capacity now? So first of all, this is 12 plus this 12, right? Then
7
what?
plus
7 plus,
plus 4.
4.
23.
Okay, nice. Take another example. Let's take
Another one will also come 23, na? Yeah, yeah. Of course, it will come 23. Same
okay.
capacities.
Let's take the opposite one. This one. No, this is capacity. This is not flow. Flow would
Got
be
it.
23 in all of them.
Yeah,
Right?
yeah, got it.
That's what
19,
we saw.
20.
Take flow out of any cut is actually same and is equal to the flow of the network. So flow would be 23 in all of them. But I am talking about capacity now. So all of this is
Yeah,
capacity.
it
Yeah.
is 34. A, B, F, E.
Okay. So 4 is
A, B, F, E.
A, B, F, E. And this is CD.
Yeah,
What is the capacity?
34.
So this edge, which is 20, and this edge, which is 14, 20 plus 14, right? That is 34. Okay, so now let's take the last one example. Let's add this also.
Whole one, only one. Yeah.
Yeah.
Is it 20 and 4, 24. A, B, C, E, F. A, B, C, E, F, and D.
This is what? 24, right? 20
24.
plus 4. 20 plus 4 is 24. Fine. Accordingly, you can take multiple examples. Take AB in one side and FECD in one side. Let's do that. Why I'm doing repeating so many is you would see now why we did that. Let's take this cut.
A,
Okay.
B.
So this is your, sorry, this is your cut. So 6 is another cut is what? AB is together and
A, B.
FECD is together, which is equal to, moving out is 16 is moving out. Then what? 4 is moving
34.
out.
34.
34 or more. 16, 4 and 14. Right? 16, 4 and 14. 16 plus 4 is 20. Yeah, 34. 34. Fine. So we had so many cuts and we found the capacity. Always keep in mind, flow through all of these cut is same and is equal to current flow through the graph. But these are capacities. These are not flows. So that's why they are different.
Mm-hmm.
Okay. Now, the thing is, if a particular cut is allowing the same amount of flow through the network, right? Whatever flow is coming is going on into the network. Any cut is actually is allowing that much flow through pass through it, right? And we just had the notion of capacity of a cut. Now, obviously, the capacity of a cut must bound the amount of flow through that cut by definition of flow and capacity. Like in an edge, the capacity of that edge is bounding the amount of flow. The flow must be lesser than equal to the capacity of the edge. Accordingly, the capacity of a cut determines the maximum amount of flow that cut can allow, isn't it? That is the definition of capacity, right? So step one, statement number one, capacity of a cut is, or let's say the flow of a cut can be equal to or lesser than the capacity of that cut. Statement number one, the flow of a cut.
One second. Yeah.
The flow through a cut. Flow through a cut, you already know. We discussed what is the flow through a cut over here, which is equal to the network flow. Any cut, any, right? That concept. So
Correct.
flow through a cut is always equal
Less
to
than the capacity.
less than or equal to the capacity of the cut, right?
Of course.
By
Yeah.
definition of flow and by definition of flow and
Correct.
capacity, right?
Correct.
Okay.
Correct.
Okay.
Correct.
So the flow through a cut is equal to or lesser than the capacity of a cut. Done. Statement 1 done. Statement 2 is when when I have reached the max flow, when the network is at max flow, right? Then any cut you take, right? Any cut you take, according to the flow of a cut, all the cut would allow that max flow amount to pass through them, right? That is this definition, that any cut would have the same amount of flow. So if
Correct.
any cut is allowing the same amount of flow and we have reached the max flow, so that means any cut, when we have reached the max flow, any cut is allowing the max flow amount of flow through it. And also any cut is bounded by the maximum capacity of that cut. Join these two statements, what do you get? The maximum flow through the network is bounded by the capacity of any cut. Now, any cut means what? Whichever cut would have the minimum capacity, that would allow the minimum amount of flow through it. If that is the case, if a particular cut is there whose capacity is minimum, right? Here you can see 26, 23, 24, 34, 34, 35. These are the different capacities of different cut. Now, any flow through any of these cuts, so let's say this 3 number cut, the flow through this cut should be lesser than equal to 23. The flow through 6 number cut is lesser than equal to 34. It would not allow a flow more than 34, right? If this is the scenario, the flow through the network is also equal to the flow through any cut that we know by definition. Now, if that is the case, I can say the maximum flow that can happen in the network is always bounded by the capacity of that cut which has minimum capacity, because that cut would not allow a flow more than that.
Once again, sir.
It should be clear.
Repeat.
Just think about it. Don't think about what I'm saying. Think about what is the intuition. The flow through a cut is always bounded by the capacity of that cut, right?
Yeah.
If that is the case, I already know that the maximum flow, whenever in the network I have maximum flow, that much flow is also happening through any cut, right? Any cut you take, the maximum amount of flow is actually passing through that cut. So when my max flow is 23, that means any cut you take, the flow through that cut would be 23, right? That we have already seen. Now, if that is the case, when will this 23 happen? This will only happen when the capacity of that cut is allowing to have it a flow of 23. If the capacity of that cut is lesser than 23, then that cut would never have allowed the flow of 23 through it. Right?
Correct.
So that means what? The maximum flow is always bounded by the capacity of the minimum cut. That whatever cut has the minimum capacity value, it is bounding the maximum flow that I can have in the graph, because that when the maximum flow is happening, when it has reached the maximum flow, that cut which has the minimum capacity must allow the maximum flow through it by definition. Because when in a graph, any cut must have the same amount of flow through the network. Now, if that is the case, then the cut which has the minimum capacity, it must also allow the same amount of flow. Even if it is max flow or whatever flow, it must allow the same amount of flow. If it must allow the same amount of flow, it must have a capacity more than that. So therefore, the concept is, if any cut, whichever cut has the minimum capacity, that is equal to the maximum possible flow that you can have in the graph. Okay, if you did not get it now, rewatch it and listen to what I'm saying 1 or 2 times and try to think what it is. It should be fairly obvious now. I mean, if you think a little bit what I'm trying to say. Okay. So therefore, the statement is the maximum flow through any flow network is equal to and bounded by the minimum cut capacity. Capacity of the minimum cut is equal to the maximum flow of the network. Now we saw all these cuts over here, right? All these cut capacity, we calculated the capacity of all these cuts in this place. 6 cuts we did. And what is the minimum among them? Tell me that.
This is the 23. Minimum is 23, but this 6 is the maximum amount of number of cuts possible, or
I mean,
more can be.
I don't know. Can there be more? Can I have anything? Let's say A, F, B. I think we
No, no,
did, right?
no, no. May or may not be, but whether we should take all the possible cuts or
Exactly.
only.
That's the point.
Okay,
Exactly. You have to
okay,
consider
okay,
all the possible cuts. Okay.
okay,
You have to consider all the possible cuts. I stopped it at this point because I already know the max flow is 23. To give you the example, that's why
okay,
I stopped.
okay. But how can we know like how many cuts are possible?
You don't have to know. Finding the maximum flow is see. You can find the when I'm saying this statement that the maximum flow is equal to the capacity of the minimum cut, or basically the cut which has minimum capacity, right? This statement is given. Maximum flow
Hmm,
through the network is equal to the cut whose capacity is minimum. I mean, the capacity of the cut whose capacity is minimum. So this is the statement. Now you can tell, okay, this is the statement. Then all I have to do is find the capacity of all the cut and then find the minimum among them. And that is my maximum flow. That is correct. You can do that. But that is a very tedious process because you have to think about all possible cuts by watching the graph. Now, if the graph has, let's say, 500 nodes, it's impossible
yeah,
to,
yeah. Then
right?
yeah, how to do
Yeah,
that?
exactly. So you don't have to do that. Why will you apply this technique? You can apply Ford-Fulkerson algorithm. That's it. The way
Okay,
we
and get the maximum flow.
get the maximum flow. That's it. Okay.
Okay,
But the
okay.
thing is, if you have to find this, I manually calculated the capacity of all this cut to give you this concept that the flow is equal to the capacity of the minimum cut. Okay. Even if you, so what I'm trying to say is, even if there were some other cuts as well, and you find the
Hmm.
capacity of all those cuts, it would not be more than 23. Okay. It would always be 23. Or, I mean, or greater than 23, or it can be 23, but it would never be more than 23. Fine. So,
No, more than 23, less than 23.
sorry, less than 23. Sorry. Yeah,
Why,
it can,
less than
yeah,
20? Yeah,
yeah,
sorry.
it can never be less than 23. It would be
Correct.
more than 23. Okay. So the maximum flow through a graph is equal to the capacity of the minimum cut. Capacity, not flow. Flow is always same as the, in all the cut, the flow is same. And that is equal to
Flow
the
is
flow of the
same,
network. Yeah,
but the capacity will be minimum,
yeah,
and that will be equal to the maximum flow.
yeah. Okay.
Correct.
And again, I would just state one more time, and I would utterly request all of you to just think about it. Otherwise, this is the main, I mean, what should I say, the main crux of the or beauty thing of this algorithm, which states
Yeah,
that
but what is the need to know this?
what is the need to
Why
know
should we
this?
know? Yeah.
Yeah, why should you know this? The thing is, you should know this because if I ask you to tell me which pipelines, right? Which pipelines, if I cut, right? So what is this cut actually telling you? This cut is
Yeah.
telling you the capacity, I mean, the minimum capacity cut is telling you that this is the maximum flow that can happen through the network. Okay. Now, this particular vertex, so let's say, let me tell this in this manner. So let's say 23 is the minimum value that I got, right? Now 23
Hmm.
is the minimum value. You find immediately, just check what are the vertices corresponding to this cut, A, F, B, C, and ED. So
Hmm.
A, F, B, C, A, F, B, and C.
Hmm. And ED.
Yeah. This is my thing, right?
Hmm.
And ED is the other thing.
Hmm.
Now, so that means if I draw a line between here,
Cut.
I can guarantee you would always find the saturated edges. That is the pipes which are at full saturation. See, just observe the graph.
Yeah.
Okay. Yeah.
Isn't it super beautiful?
All the edges will have this saturation because it is the minimum one, correct?
Yeah.
Because the maximum flow has been achieved, so minimum one will be there, right? Okay, correlating, yeah.
Right?
Correct.
So
Correct.
that's why this is important. Now, if I ask you in a pipeline network where, let's say, in a steam engine kind of, or not steam engine, what I mean is, let's say, a thermal power plant where high pressure steam is used, right, to rotate turbine to create electricity. In that kind of a setup where pressures are very high, I tell you,
Mhm.
I ask you this question: which are the pipes which are at maximum risk of getting punctured or getting into trouble? Obviously, those pipes which are at their maximum capacity. Now, if the network is very
Correct.
complex, you don't know which pipes in a complex network are at maximum capacity. So you can have a blueprint of the map, and then you can apply Ford-Fulkerson algorithm, and you find that if the setup is working at its maximum efficiency, that means it is at its max flow. Then these pipes are at maximum risk of getting corroded or getting punctured, because these pipes are the saturated pipes. That's where the concept of min cut comes.
Yeah.
Right?
Correct.
See, any pipe which is working at a which in which the flow is lesser than the capacity, in those kind of pipes, the risk of getting corrosion or other kind of problem is less. But which is
Mhm.
very fully saturated, those pipes should be under high maintenance all the time. So you need to find those links where the whole bandwidth is used up or whole capacity is being used up, right? So that is given by the min cut. As soon as you find the cut, you can just draw the set and see what are the edges which are between these two set, and you can find those edges are always the edges
Yeah,
which are at full
but
capacity.
here the graph is small. Suppose if the 500 or 1000 nodes are there, then the algorithm will give the solution of the which sets are giving the minimum flow.
Sorry, what did you tell? Yeah. Uh,
I tell suppose 1000 nodes are there,
yeah.
then this Ford Fulkerson algorithm will give
Max flow.
all. It will give the max for all the cuts. It will give this
Yeah.
algorithm will give.
The algorithm will give only the max flow. You have seen it, right? Just the max flow. It would not
No,
give the.
no, 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 no. Max flow. It will give
Yeah.
by the algorithm. Then how we will get the this sets, the cuts?
Okay.
Okay,
So that's.
which node is giving the max flow?
Yeah. So that's what I'm saying. From your exam perspective, I'm telling you, from your exam perspective, one graph would be given, and I would answer the practical perspective also. But from your exam perspective, let me tell this. First of all, a graph would be given, and two kind of question can come for the same flow graph. Either the max flow and then or the minimum cut. What is the minimum cut or what is the maximum flow? The max if they ask you the maximum flow, all you have to apply is Ford-Fulkerson algorithm and write the answer. If they ask you the minimum cut, now obviously the
Okay.
graph in this case is a small graph, you are solving on it. So once you have completed the Ford-Fulkerson algorithm, this graph you would achieve. Now once you see this graph, you can anyway see what are the edges which are saturated. I mean, through visual inspection. That's why I said that from your
Okay. And I cut
right,
that one.
just
Right.
you can see that 12 is saturated, 7 is saturated, 4 is saturated.
Yeah.
So
Got
basically
it.
that means the cut must be something like this. And once
Just,
you
just, just take the edges which are saturated.
yeah,
Yeah,
and
yeah.
draw a line through cut to cut all of them, all the edges, all the saturated edges. That means ED
Got
is one and this is another. So this is your cut,
Got it. Yeah, I got it.
right? So this is exam perspective. And now real life perspective, how it is done is you apply Ford-Fulkerson algorithm, you get the min cut at first. That is easy to do. Once you do that, either you can traverse the graph in order time, right, by any BFS, DFS or whatever, and check which are the edges which are basically saturated.
Saturated. Yeah, got it.
That's it.
The same.
And
Yeah. This trick we can apply in that. Yeah.
yeah,
Another block of code it will do.
exactly. Yeah.
Mhm. That is very useful thing, I think, in the
And
real life also.
yeah, it's greatly useful. And
Great,
it's
really.
right.
Sir, why do you say ED is saturated if because it is 19 and 20 is there?
ED is not saturated. Who said ED is saturated?
It's not saturated, right?
No. Only the boundary edges, which are the orange line which is cutting, just see
Yeah,
those. Yeah.
those are saturated. Yeah.
Yeah.
Okay.
It is within the set, right? It is inside the set. So let's say any edges between AF, FB, BC, FB, whatever it is, any inside this, right? Inside this set or inside this set, I would not consider those edges. From here to here, right? That I would consider.
So
Those
the
are
edge that is connecting, that is going through our
going through. That's
yeah.
why, remember in the previous diagram, I wrote S1, S2, and
Yeah.
like this, two are coming. So yeah.
Yeah. Okay, got it.
Correct. Very nice.
Okay.
Real life solution it will come through this.
Fine. So that was your Ford-Fulkerson algorithm. And just one more time, I am stating this fact, why this maximum capacity thing is working. Because the capacity of a cut is binding the flow through the cut. Point number one. The flow through any cut is equal to the flow through the network. Okay. The flow, since the flow through any cut is equal to the flow through the network, when the network has reached maximum flow, accordingly, all the cuts, right? All the cuts must have that much flow, which is equal to the max flow. So at max flow condition, all the cuts.
Once again, pardon.
Just think, any cut should have equal flow, and that flow should be equal to the flow of the network. Isn't it correct? We
Yeah.
have already discussed that.
Yeah.
So any cut you take, any cut, random, any cut you take, that should be equal to the flow of the network, and all of them would have the same thing, which is the flow of the network, right? Flow through that cut. Now flow through a cut is always bounded by the capacity of that cut, right? Flow through a cut is bounded by the capacity of that cut, like flow through an edge is bounded by the capacity of that edge. Like that, flow through the cut is always bounded by the capacity of that cut. So if flow through a cut is bounded by capacity of that cut, and any cut must have the max flow, any cut must have the max flow when the network is at max flow. Therefore, capacity of that cut which is minimum, right? The capacity of that cut which is minimum, that is binding that cut to have any flow which is lesser than its capacity. Now, since all the cut must exhibit the max flow at the max flow state, that's why the cut which is having the minimum capacity, that is binding the maximum flow. If you don't understand what I said just now, just listen to it 2-3 times slowly and try to think each thing that I'm saying. Once you get it, you would say, okay, it's obvious. But if you listen to the whole thing, it might get a little bit complex to understand. But if you have understood what I did on the screen till now, just think this statement, what I said. It would be very obvious once you just pay some attention to it. Okay. Now, so max flow, min cut, and these things are done. From your exam perspective, I also told what kind of question might come. Given a graph, you have to apply Ford-Fulkerson algorithm. They would ask you either the max flow, or if they ask you the max minimum cut, all you have to do is just see which are the edges which are saturated. Just put a line through all the saturated edges, and you would get 2 parts of the graph. Those 2 parts are basically the minimum cut, right? It would, in the option, one of them would be there. So that's done. Okay. Now, there are some problems with respect to Ford-Fulkerson algorithm with respect to time complexity, which is basically when we are figuring out this augmenting path, right? If I figure out a path where the bottleneck capacity is very less, then my addition with bottleneck capacity would be very less every time. And that's why the iteration, number of iteration would be much more, right? So that's why how to choose a path so that I can get a bottleneck capacity which is comparatively more. I don't end up with the worst case scenario. The thing is, since this is flow conserved network, right? This whole thing is conserved flow. If I get a path which is of minimum, not minimum, or let's say, yeah, minimum only. Let's think of a path which is of least number of halts in between. That is of minimum number of edges. If a particular path has minimum number of edges, and since along that path the whole flow is traveling, therefore there is a high probability of chance that I would have the higher value weights along that path because the edges are less, right? If the number of edges are less and I'm traveling and I'm carrying forward a constant amount of water within lesser number of edges, that means along that path more water is being carried out by each edge. right? A particular path is there where 10 edges are there, and another path is there where 3 edges are there. Both of them are carrying, let's say, 20-liter water. So that means what? The path which is having 3 edges is each pipe in that path is carrying more water. That is obvious, right? So therefore, while for finding the augmenting path, if I want to ensure that my bottleneck capacity is not the least possible value, then I have to find that path which has relatively lesser number of edges. That would ensure the capacities are more along that path. So therefore, if I have to find lesser number of edges path from A to D, source to sink, then we can do what? Which algorithm gives us path with least number of hops or least number of jumps between two destinations? Which graph traversal algorithm gives us least number of hop path or jump? How many?
BFS.
BFS, correct. So therefore, in order to find the augmenting path, we apply the BFS algorithm. Okay. When you write the code, if you write so in week 11, we don't have coding, but let's say you write the code for Ford-Fulkerson algorithm, then once you draw the residual graph over here, right? So then you have to find the path. In order to find the path, the algorithm that you would use is BFS. So once you use BFS, you are somewhat guaranteed to get a path which is having a better value of offset. So that when you add this offset, you get to the convergence state much faster. You don't add 1 or 2 every time, and it takes a lot more iteration. You don't end up with that, and that's why we use BFS. That is one shortest path, exactly. So this has again been discussed in the lecture, and you can check that over there once again. But this residual graph and all this min cut and all these things are not in that much detail. So this is very important to understand it from here. Okay, and again, since if you take this, so if you take the worst case offset every time, right? The minimum offset. If you choose a path whose offset is, let's say, 1 or 2 or something like that, right? That offset means the minimum edge weight along that path. So the minimum edge weight along that path is very less, 1 or 2. So your addition in the original graph would always be less, +1 or +2. So that means if you are adding by 1, 1, 1, 1, and let's say your actual answer is in thousands, so that means you would need 1,000 steps.
Complexity will increase.
Exactly. So the complexity of your Ford-Fulkerson algorithm, if you do not use BFS, then the complexity of the algorithm of Ford-Fulkerson, that is order of, let's say, not order of, the complexity of Ford-Fulkerson algorithm is directly proportional to the highest capacity of pipeline. So if your sum offset is 1 and a particular particular edge is there whose capacity is, let's say, 1 lakh, right? Some edge is there whose capacity is, let's say, 1 lakh, right? 4, 5, 6, 5. So let's say something like this. One edge is there, and every time you are adding by 1, which is the offset. So your iteration would go on 1 lakh time. So the complexity of Ford-Fulkerson algorithm is directly proportional to the highest capacity of any pipe that you have. Now this is very bad because highest capacity is a data, right? It's not anything number of steps. And in our initial week 2, we discussed, we always try to write complexity in forms of the number of steps of an algorithm. But here we saw that the complexity is directly dependent on the highest capacity. Highest capacity is nothing but the edge weight, which is a part of the data. So depending upon, even if a small graph is given to you, right? Like in the famous example, which is there in the lecture in many books, like something like this, a path is there, right? And these are 100, 100, 100, 100, and this is 1. This is your source and this is your destination. Now, if I take this path always, right? So 1 would be the offset value, bottleneck value. So every time I would add 1 over here, then add 1 over here, like that it would happen.
Yeah, right. It will take 100 times.
So that means what? 100 is a data point. It's a data characteristic. It's not anything number of steps, or it's not inherent to the algorithm. It is inherent to the data that I'm giving. So even for this small, let's say this 5 nodes or 1, 2, 3, 4 nodes graph, this 4 node graph, it would take 100 iteration to converge. And let's say if in place of 100, I would have written over here 2 to the power 40. Can you imagine? For this 4 node graph, I would iterate for 2 to the power 40 times.
It will hang up.
Exactly. So that's why even for such a small data set, it is getting so many iterations. That's why it is very important for us to use BFS and find the path which has shortest number, least number of edges, and that's why a greater of bottleneck value.
We will not do coding for this, no?
No, no.
Okay. And BFS, we will apply BFS in this?
Yeah, if you apply BFS, then you are guaranteed the offset would be more and you would get a better path. So in this example also, if you take, right, in that example that we just discussed.
How to implement BFS in this?
How to BFS is normal BFS. Give the A as source and D as destination, and it would give you the.
Okay. Yeah.
Sir, highest capacity, when you say, you mean that capacity in the entire graph or in the capacity in the path, argumented path?
When, in which respect highest capacity?
So Ford-Pruckson algorithm directly proportional to highest capacity. So highest capacity, when you say, you mean entire graph?
I mean entire graph.
Okay. Suppose in the bottom side, if it was 14,000 or something.
Okay.
Then it would we won't consider this into the argumented graph, right?
Okay, so now so if the bottom part is somewhere 14,000 or 4 lakh or whatever something was there, but you don't know whether the algorithm will converge in this, right?
Right.
Let's say in some subsequent step, your augmenting path is actually getting through that 14,000 path, then it would consider that, no?
Yeah.
So
but
that
in this case, if 14,000 was there, it wouldn't affect.
No, in this case, it wouldn't affect. Yeah.
Yeah, but in general cases, we cannot assume that.
Correct.
Okay. We are thinking about the worst case.
Yeah.
Correct.
So, like if you apply BFS in this example that we had, right here, 1 is the capacity, here 100, here capacity is 100, here also 100, here also 100. Fine. This is your destination. This is your source. Now, if this is the case, if you apply BFS, so BFS will guarantee that you find this path or this path, because these are two edges path. BFS would ensure you do not end up with this one, because this is 3-edge path, right? And BFS always gives you shortest path, shortest number of hops path. So it would ensure this path. So if you go through this path, if this is your augmenting path, then your offset is 100. So in one iteration, it would converge 100, and then it's done.
Correct.
Likewise. Fine. So that was the complexity part. Ford-Fulkerson algorithm, all these things done. Now, now this is again a very important point, and now whatever I would say, the statements are most important. We don't have any algorithm or that kind of thing over here. It's a theoretical discussion mostly. So this is what we call the complexity theory or complexity classes. Fine. The fundamentals of this discussion, complexity classes and all these things, is based upon another subject of computer science that we will not discuss, and it's not there anywhere in your whole program. So not even in the degree level, it's not there, because that part is core computer science. It's fundamentally conceptual concept. It's not anything which is applicable. It is applicable actually. All compilers that you use, those compilers are designed on the basis of the concept of this subject. And this subject is what we call the theory of computation or automata theory. Okay. Theory of computation. Not architecture.
It is related to okay.
No. It's not related to architecture. Architecture is totally different. It's a theoretical computer science subject, which is what we call the theory of computation. That how computational machines work. What is the fundamental mathematical model for that? What is the mathematical model for a computing machine? Okay. So that's what it deals with. That is what we call the automata theory or theory of computation. Okay. So those of who you are there in CS, CS core courses like BTech or something, you would learn this subject hopefully in your second year or third year. Maybe not in third year, second year only. So anyways, but that is not there. But that subject lays the foundation for complexity classes, and we are getting into complexity classes without learning that subject. So therefore, these complexity classes we would be doing on a very superficial manner. And what's important for you is to, whatever I will discuss now, just observe that, keep the statements in mind. If you can do that, you would be able to answer the question. You don't have to go into very depth, because at some point you would get stuck if you don't have the idea of this Turing machines and all those things. I mean the theory of computation part. So let's try to address this. I would try to discuss this in as application oriented manner as possible. So what is the concept of this whole this topic, or this, that we are trying to segregate the problems that we solve in algorithms into different classes, right? We would classify the problems, like those of you have done machine learning, you did classification, right? And accordingly here also you would try to classify different problem statements into different problem classes, which we call complexity classes. Now, what is the basis of this segregation or basis of this classification? The basis of this segregation is complexity of the algorithm. That is it difficult to solve or is it easier to solve? Now, what is the definition of difficult to solve and what is the definition of easier to solve? Definition of easier to solve is it should be solvable as a polynomial time algorithm. So the problems which I can solve in polynomial time, those would be there in one class. The problems which, so let us keep it at this, that the problems which are solvable in polynomial time, they would be there in one class. And those problems which are
Polynomial time means
anything which is whose order would be either n to the power some k. K can be equal to anything, right? K can be very, very large. K can be towards not infinity, because then it doesn't make sense. What I mean is K can be very, very, very large. It can be something like 2 to the power 100. It doesn't make any difference, right? But it is some n to the power some constant. Basically, that's the point. Now, when I say n to the power constant, is this statement correct? Let me write this statement. Is this statement correct? This is correct, because what is this? This is n to the power 100 into log 100 n, right? So obviously, I can always say that n to the power 200 is always greater. Fine. So therefore, this definition is correct. So when I say n to the power k, don't assume every algorithm which is some n to the power some 2, n cube, n4, or n to the power something is coming into the
equal to is how it is correct. Equal to sign.
Order means what?
Log n to the okay, order. Yeah.
Right.
Order means it's the order of the two n.
Yeah. So n to the power k means log n also. Log n is also equal to order of n to the power k. Right. So always keep that thing in mind. When I say that any problem which is solvable in polynomial time, that means log n problem also. Don't think that only n square or n cube or n order nk. I mean order n. Order n, I mean log n, anything, n log n, whatever you have, all those things should be.
That means like from monomial to binomial, trinomial, everything.
Exactly, anything. Logarithmic, monomial, mix of logarithmic and monomial, or by any polynomial, right? Polynomial with a logarithm, still only polynomial, only logarithm, anything doesn't make a difference. So these are all solvable in order nk time, where k can be very, very large. I am allowing you to have a k of very, very large value. So whatever is let's say I tell you log n to the power 500, you write okay, n to the power 200 or n to the power 500. That would be order n to the power. So anything which is solvable in polynomial time is coming under the P class. It's what we call the polynomial class. Okay. So on the basis of complexity, how much difficulty it is to solve a problem, we are segregating problem into different classes. Right? Now, so this is the universe of problem. From this universe of problem, I have two parts. First one is Now, what is this undecidable problem? Not in our syllabus, not in our discussion, because this domain is completely belonging to theory of computation discussion. Okay. So this is not in our discussion. Undecidable problem, what are these? But if you have heard about it, someone has heard about it, I'm telling you one line. So your halting problem, if someone has heard, is one such problem. Halting problem of Turing machines. So that is an undecidable problem. What is undecidable problem? We will not go into that. Our domain of discussion is in decidable problem. So what are decidable problem? Basically, you can think of it in this manner, that decidable problems are those problems for which
Turing
answer.
machines means? Turing machines means?
No need of discussing those things.
Okay,
Halting
okay,
problem,
okay.
Turing
Forget.
machine. That's
Okay,
what I said.
forget.
Right? Yeah, forget
Okay,
about
okay,
all this. Just for
okay,
sake of completeness, I draw this in this diagram. Right? For
okay, okay.
any problem, universe of problem can be decidable or undecidable problem. Undecidable problem is not in our discussion. Okay.
Okay, okay.
Decidable problems are those problems whose answer you can get. That is, you are certain to get an answer, but you don't know how much time it would take. Now, how much time it would take, on the basis of that, I have two segregation. The first is tractable,
Mm,
another is intractable. So these intractable problems are basically those problems which takes more time. And tractable problems are those problems which are taking less time. What is the meaning of less and more? The concrete definition is those are solvable in polynomial time. So basically this means
okay, okay.
problems
That can be solved by an equation. Equations.
solvable in polynomial time. And again, I just repeat it, polynomial time means log n, log n square, n log n, all those things also. Okay. Problem solvable in polynomial time. So these are tractable problems. And therefore they belong to, and basically the class. So discussion is complexity classes, right? We told that we would segregate the problem in different classes. So the class corresponding to this tractable problem is P class. So all this problem is what belongs to the P class algorithm. So all the problems which are solvable in polynomial time, we will put them under the P class. Done. Okay. Now you have to be very, very, very careful. What are intractable problem? The definition of intractable problem. Again, the definition of tractable problem. Tractable problem means P class. Just think in this way. Okay. The definition of tractable problem is, or the definition of problem which belongs to the P class is, any problem which is solvable in polynomial time. Done. Simple thing. Now, what is the definition of problem which belongs to the intractable section or NP class?
Non-polynomial class.
So the definition is problems which are solvable, or let's state it in the other way, which are not solvable in polynomial time. Or you can also say problem which are solvable in non-polynomial time. Right? Either of these two. Right?
Sir,
Actually,
constant time will be also
polynomial time. Anything, because
okay.
again I said, right?
Constant is also there, right?
Constant, any constant is equal to order of n to the power k.
Yeah. Okay.
Right?
Mm.
So, but the thing is, this is wrong. So, yeah, that is wrong. P class problems are problems which are solvable in polynomial time, but NP class problems are not those problems which are not solvable in polynomial time. The definition of NP class is not that easy. P means solvable in polynomial and NP means for solvable in non-polynomial. That is the greatest mistake every one of us make when we are studying this for the first time, right? P is correct. P's definition is correct. It is solvable in polynomial time. But if you say all those problems which are not solvable in polynomial time belongs to the NP class, then that is a wrong definition. In fact, it's totally wrong. That's why I wrote it explicitly. And again, I am explicitly stating this is a wrong definition. Do not write or do not tell or do not in any phase of your exam or your life or anything, do not tell that NP class problem or those problems which are not solvable in polynomial time belongs to the NP class or are intractable. That's a wrong definition, right? So what is NP class then? Let us keep it at blank. Just as of now, keep this thing in mind that it's not that the problem which are not solvable in polynomial time belongs to NP class. That's a wrong definition. What is the right definition? In order to address that, we have to at first learn something else. So we would do that. By the way, some examples of this P is, let's say, Dijkstra is solvable in polytime, right? You did Dijkstra was order of E log V you can do. Or let's say any dynamic programming that you did, like let's say matrix multiplication, n cube time, right? Matrix multiplication. Let's say what was the complexity of Prim's algorithm? Again, E log V. So Prim's algorithm, your E log V was the time. So again, those are polynomial. So all these things are tractable problem, polynomial time problem. Intractable or NP class problems are what? Basically, as example, I told you the definition we have not yet done. We would do that after some time. But examples of NP class problems are those problems which are generally taking you exponential time, some 2 to the power n complexity, or n to the power n complexity, or n factorial complexity, or some any constant a to the power n complexity. So those are the problems which are intractable, right? For example, but I have not yet told you the definition of NP class. We would come to that after some time. Okay, so now again come to this point. We would learn a new concept which is we call the checking algorithm. Or someplace you would see we call it verification algorithm. Okay, checking algorithm or verification algorithm, both are the same thing. Some places call it checking, some places call it verification algorithm, some places also call it certificate algorithm. Okay, what is it? It is stating that given a problem and an answer to that problem, you have to tell me an algorithm to verify whether that answer is a correct answer for that problem or not. Take an example. I have given you a Boolean expression, right? By the way, you guys know Boolean expressions, right? Boolean algebra or anything?
Yeah.
I mean, as a part of BSc degree, was it taught?
At some point, yes.
Okay, yeah, that's what I'm asking. So let's say I have a variable, an expression. Let's say A complement B plus C D complement E plus C complement A complement E F plus.
We have not gone through this Boolean.
Okay, let me just, some not very difficult. What I'm saying is, let's say we have an expression like this. Now, okay. Okay. There is again, Shashikant, some background noise is coming up. Please mute. Okay, so each of these variable A, B, C, D, E, right? So this is what? This is basically a function of, right? Now each of this variable A, B, C, D, E, F is also there, na? F. So each of this variable can have either 0 value or 1 value. That's it. That is what we call Boolean algebra. A bool, I mean, two things are there. Boolean logic, right? True or false. So something like that. So either each of these variable can either be true or it can be false. Or basically you can tell that either can be 0 or it can be 1. Only two values are possible. And this dash means complement, right? If it is, if E and E complement are, if E is equal to 0, then E complement would be equal to 1, right? Now the question is, given this function, given this expression, I want it to be equal to true or 1, whatever you want to tell. So this is my question. Now if this is my question, if this is my motive, right? My question is not my question. The motive is I have to get it to 1. The question is, what are the assignments? What are the assignments for each of the variable? Fine. So you tell me whether A is equal to true or false, B is equal to true or false, C is equal to true or false, D equal to true or false, E and F equal to true and false. What are the assignments for each of these variables so that this whole expression boils down to true or 1? When I'm writing C A, that means C dot A, that means C and A. So those of who you know this, I hope it should be understandable. Those who don't know, okay, don't worry. Just it's like this, right? It's an into thing. You can assume it as into only, A into B. Okay, and these are plus, normal plus. Assume it like that. Only there are rules like 0.0 equal to 0, 0.1 equal to 0, 1.1 equal to 1, 1.0 equal to 0, right? And 0 plus 0 equal to 0, 1 plus 1 equal to 1, 1 plus 0 equal to 1, 0 plus 1 equal to 1. So these are the two. This is and or dot, and this is or plus. By following these rules, you can, I mean, you can solve this expression. Doesn't matter, but what I'm trying to say is you have to bring 1 or true. Now my question is, what are the assignment for each of these variable? Can someone tell me what are the number of possible assignment that I have? Number of possible assignment. I don't want the true, I mean the assignment for which I would get true as the result. What I'm asking is, what are the, how many possible assignment are there for these many variables? Can someone answer that?
2 to the power 6.
To the power 6?
64.
Are you sure?
I mean, what are the possibilities, right?
Correct.
So, like, A can be true or false, B can be true or false, C can be true or false.
Exactly. Yeah. So that's the logic, that every variable can be either true or false. So there are two options for each of the variable, and I can have, therefore for A it can be 2. When A has two choices, and at the same time B also has two choices, right? So 2 into 2 into 2 into 2, 6 times for all 6 variables. Therefore 2 to the power 6 number of possibilities are there. So if I have a function of n variable, here it was 6 variable. If I have a function of n variables, so then I would have 2 to the power n number of possible, what should I say, enumeration, or 2 to the power n number of 2 to the power n number of assignments. Now I take any one of this assignment out of this 2 to the power n and put into this expression, right? And then I solve the expression. Once I put a particular assignment, choose an assignment and put the variable values, and then I solve that expression. Once I solve the expression, I would get the result, right? And I can check what the result is. Is it true or is it false? Okay.
What does it mean? I did not get this.
Since you don't know Boolean algebra, you
Okay,
cannot, you
okay,
would, yeah, you would not
okay,
be able to
okay.
solve it. But the idea is, we can take any of the 2 to the power n possible assignment of these variable values, right?
Hmm.
And we
Hmm.
can put the variable values into this expression and solve this expression, right? And
Any one set out of
any one assignment, right? Any one
that.
assignment, any one of the
Hmm.
assignment out of this 2 to the power n I will pick and solve, put it here and solve it, and I would get the result, and I would be able to see whether this is true actually or false. Then this whole thing boils down to true or false, right? If it boils down to true, that's the solution. That's where the Boolean algebra comes. But if you solve it, you would either get true by solving it, or you would get false. If you get true, then it is matching. If you do not get true, then again you have to pick another assignment from the leftover 2 to the power n minus 1, right? From that assignment, you can take another and then again put into this and try to solve it. Right?
Okay, all the possible cases we will start by trial
Exactly.
and error, whatever.
Exactly.
Okay.
So in
Okay.
worst case scenario, if the last assignment is the correct one, so there would be 2 to the power n number of cases you are putting into this expression and checking, and the time taken to solve this, once you have picked a particular assignment and you are putting the value and then you are solving this, right? So the time taken to solve this would again be equal to the number of into and plus you have. Okay, so then again that would be some function of your n, right? It can be linear time also, depending upon if you have a specific form, then it would be 2 to the power n into n.
Hmm.
So what I mean is, whatever it is, this is the time that it can get. I mean, it is coming into this exponential time. To solve a problem like this is actually what we call the satisfiability problem, SAT problem, which is there in the lecture. Check it out. This is called SAT problem or satisfiability problem. That is, we are trying to satisfy this function, this expression, Boolean expression. Okay. So it would take you exponential time. So to solve a satisfiability problem, it might go to the exponential time situation, right? But now I'm not telling you to solve it. Now I have changed the question. Now I am telling you, see, probable answer. Mr. Srikanth, can you mute again, please? Yeah.
Yeah.
So f is false. So let's say I give you that probable answer is this thing. I give you the expression, I give you the question, it should be true, and I give you this is a probable answer. And now ask you the question. The question is, tell me whether the answer is correct. Whether the answer is a real solution of the problem. That is, I'm telling you to check whether or verify, check or verify whether the given this answer, probable answer, is actually a solution to the problem or not. So what I'm trying you to tell is, you take this value, take this assignment, put it into the expression like you were doing earlier, and tell me whether the result is true or false. If the result is true, that means it is an actual solution to my problem. If the result is false, then this is not a correct solution to the problem. Got the point? So that is what I'm trying to tell you. Don't have to solve the question. I am giving you a question as well as an answer. All you have to do is give me an algorithm to verify or check whether the given answer is a real answer to the question or not. Check whether the answer that I have given is actually really an answer to the question or not. Whether it is getting true, whether this assignment is getting me value true or not for the expression, for this expression. Now, how much time would it take you to write an algorithm to do that or solve that? It would take you some order polynomial time only. Why? Some function of n time. Because remember, in the initial case, what did we tell you? The 2 to the power n would be the number of enumeration. That is fine. But once you get an enumeration, to solve this, it would be some function of n time. Right? Because you have put the values, all you have to do is compute this into and plus. Okay, now if you have this into and plus, if you can do parallelly, so all these terms would be happening in parallel. This and this can happen in parallel. Right? You can do those things in parallel. Once you have done all of that, you can do the addition accordingly. So once you got the assignment, right? You given an assignment, or the time required would be directly proportional to the number of multiplication and addition that is there in this expression. Right? So therefore, that can be done in some function of n time. It's not 2 to the power n. 2 to the power n was coming due to the number of possibilities. But once I've given you a specific allocation assignment, then it would take you order n or some order n square or some function of n time. So then it is not it's not taking more time or exponential time, and that's why it's not interactable. So verification algorithm and checking algorithms are not interactable algorithm. They are algorithms to check whether given a problem and given a solution to the problem, whether that solution is really a solution to the problem or not. Right? So that is the definition of verification or checking algorithm. Now if again, I don't think you guys, so in graph theory, you have learned Hamiltonian path, Hamiltonian circuit, all those things or not? Eulerian path, I think you all must have learned. Hamiltonian path learned.
Hamiltonian we have learnt, but I think we have not used so much. We have learnt in the graph theory, Hamiltonian word came, and somewhere I do not remember exactly what.
Yeah, I'm also remembering it, but I do not actually remember.
But it was not used anywhere.
Yeah.
Okay.
The lecture.
Okay,
Am I right
fine.
now?
No problem, fine. So maybe we can skip that. But basically, what I was trying to say is, I would give you another example. So, given a graph, if I ask you that find
Just explain in one line so that we can.
Hamiltonian, so Eulerian circuit or Eulerian path, do you remember?
No, it was not there.
Okay, given a graph, what is an Eulerian circuit? An Eulerian circuit is a circuit, right? Or let's say we would call a graph. Let's state in this manner. Given a graph, we would call that graph as an Eulerian graph, right? If you can travel through all the edges of that graph without repeating any edge. Okay.
Mm-hmm.
Without repeating any edge, you travel through all the edges of the graph. All the edge, that is point number one, all edge. You should not leave any edge. And second thing is, you should not repeat any edge, right? You cannot repeat edge, or you cannot leave any edge. You have to cover all the edges. That is Eulerian graph. Hamiltonian graph is what? Hamiltonian, we would call a graph Hamiltonian graph. If you start from one point, one vertex, you cover all the vertices without repeating any vertex. Okay? You cover all the vertices without repeating any vertex. Okay? So Eulerian is
what is difference between?
That's what you have to think. I mean, is it same or is it different? Euler says you can cover all edges without repeating any edge. What Hamiltonian says, cover all vertices without repeating any vertex. Okay. And what is the difference? That is that's what that comes into the graph theory part.
Okay. Age and yeah.
That is that. Okay. That is the over. I mean, from overview you see that okay, it is edge and it is vertex, but there is a much more subtlety into these two concepts. But anyways, so if Hamiltonian graph is a graph in which I have to travel all the vertices without repeating any vertex, and I've given you a graph and asked you whether this graph is a Hamiltonian graph or not. Okay. Or I have asked you, okay, then Hamiltonian cycle would also come. Anyway, so let me tell you that given this graph, it is a Hamiltonian graph or not. Then checking for that is again a very difficult problem. But if I ask you what is a Hamiltonian cycle, that also is a difficult problem. But if I give you a particular cycle and can try to tell you that whether this cycle is Hamiltonian or not, that is easy to check. Okay.
Yeah, we put the value of that.
Put the value. Yeah. So once I give you an probable answer to check whether that answer is correct or not, that algorithm is called the checking algorithm or verification algorithm.
Got it.
Okay, fine. So now coming back to like in this example, if I tell you what are the correct assignment, then it had 2 to the power n possibilities. It was some exponential time taking process. But if I give you this particular probable answer assignment, then you can just use, put this value and do this dot and plus and you would get the result. Doing this dot and plus would take you some polynomial time, and that easily it can be done. Okay. So therefore, these are checking algorithm. Now coming to our previous, just a second. Now coming to our previous point where we left, that what is the definition of NP class? The definition of NP class is okay. This is the definition of NP class. Those algorithms for which a polynomial time verification algorithm exists, those problems belong to NP class. What is not the definition of NP class? Problems which are not solvable in polynomial time. This is not the definition.
Okay.
Fine. This is not the definition of NP class. NP class's definition is problems for which polynomial time verification or checking algorithm exists. Okay, but problem solvable in polynomial time is belonging to P class. That is correct. But problem solvable in non-polynomial time belongs to NP class is wrong. Problem which are not solvable in polynomial time belong to NP class is also wrong. Okay, NP class is not easy as P class. Therefore, you cannot directly say that. Definition of NP class is problems for which polynomial time verification or checking algorithm exist. I am not telling anything about the real problem. I am not telling that, okay, that how much time would it take you to solve the SAT problem, right? Here we discuss, this is the SAT problem.
NP class is not solvable, but it exists. This is the definition, right?
No. NP class is not solvable means?
In P class,
Yeah.
solution in polynomial time can be solvable, right?
Correct.
But in NP class, it is not solvable, but solution exists. We have to just check by verification, right?
No. Just a minute. See, solution exists in both cases. Now in P class, to find the solution of the problem, it takes you polynomial time. In NP class, to find the solution of the problem, as of now, so please now let me tell you this in this manner. In NP class, as of now, please underline this term, as of now. As of now, in NP class, the solution, in order to write the algorithm to find the solution to the problem, it takes non-polynomial time. As of now, I'm again saying, in P class and NP class, both these classes, the problems which are there in both these classes, solutions exist. Solution exist or not exist, that question comes in undecidable problem. Decidable problem, solution exists. That is P. Now in P class, the solution can be found in polynomial time. In NP class, as of now, it is observed that the solution cannot be found in polynomial time. As of now, it is observed that the solution cannot be found in polynomial time. But as soon as I say the solution cannot be found in polynomial time, I am wrong. I can only give you the, that's why the definition is this in this format. The definition is not in the format that NP class problems are those problems for which, as of now, the solution finding takes non-polynomial time. This is not the, when you put as of now or something, it cannot be a definition, right? It's not something formal to say. That's why the formal definition is this. But to get the essence of it, I am telling you, as of now or till date, it has been observed that NP class problems constitute those problems which takes this exponential time or non-polynomial time. Okay, got the point. If I tell you the definition is NP class problems are those problems which takes non-polynomial time or which are not solvable in polynomial time, that is a wrong thing to say. I I can tell you as of now, it is observed that those problems which belongs to NP class takes non-polynomial time or are not doable in polynomial time. But as of now, it is observed. That line is very, very, very important. If I just remove that as of now, it is observed and directly tell you the definition is problems which are not solvable in polynomial time, that is a wrong thing. Okay, because this is an open question. If you can solve this NP duality problem, you would get $1 million and hopefully a Fields Medal, so, or a Turing Award, which is the Nobel Prize in Maths and Computer Science respectively. So yeah, it's an open problem. That's why I'm saying this is an NP class. What is the, can I tell this, that problems belonging to NP class are those problems which are not solvable in polynomial time? If I can tell this with full confidence, then I have to prove it. It's not yet an open problem. Sorry, it's not yet a, I mean, it's still an open problem. Okay. So anything regarding this, I cannot say. What I can say is, if I have to write the definition of NP class, then I can tell at most this thing, that problems for which polynomial time verification checking algorithm exist. Okay. Now, but again, I hope you got the idea, because these are the examples of NP class complexity. So I can tell you informally that as of now, it is observed that all the problems which belong to NP class, or I can also state in the other way that as of now, those problems which are not solvable in polynomial time, we put it into NP class as of now. Okay, as of now, those problems which are not solvable in polynomial time, we put it into NP class. But
Yeah,
that,
this one is okay. This one is okay.
as of now, again, you don't know how much stress I'm putting on those words, because
As of now.
yeah, as of now it is observed, because if I don't write it in, if I don't tell you
in future, NP class problem can go to the polynomial class also, right?
Yeah,
What do you
exactly.
mean to say, right?
Exactly.
Whenever we get, then it goes to the jumps to the NP class. Is it so, no?
Exactly.
Yeah.
Right?
Yeah.
But I cannot put it into definition because it's yet not proved.
Yeah.
So P class's definition is it, problem solvable in polynomial time, simple and straight. But NP class's definition is this, problem for which polynomial time verification or checking algorithm exist. Okay.
For example, you can say that like a coronavirus solution. Suppose we get, then it is come to the P class, right?
Yeah.
Right now, it is like that, no?
Yeah. Essence is like that.
Right? Yeah, essence is like that. Okay.
Now
that is why it is called intractable.
Yeah, that's why it's intractable. But vaguely speaking or informally speaking, whenever you see this n to the power n, 2 to the power n, this exponential algorithm, they belong to intractable or NP class problem. That is which takes more time. Polynomial, this exponential time, right? These are very high time complexities. So they would, therefore, they are intractable problem or they belong to the NP class. Okay.
Right, sir, right.
Okay, now this is the whole tree structure of this. Now let us have a set diagram, and this is the final thing for today's discussion. And this, so we know about P class and we know about NP class, and we have seen verification algorithm. Verification algorithm is given an algorithm, you are trying to given a problem and a solution, you are trying to check whether that you are writing an algorithm that checks whether the given solution is really a solution to the problem or not. And on the basis of this new tool, which we call the verification or checking algorithm, we wrote the definition of NP class, formalized it, that all those problems for which a polynomial time verification algorithm exists, right? Those problems belong to NP class. So when I say the satisfiability problem, SAT problem itself was order of 2 to the power n into some function of n, right? We saw that. So therefore it is belonging to NP, it is intractable. It has a complexity of this exponential complexity. But I can only say that the SAT problem belongs to NP class when the SAT problem also has a polynomial verification algorithm or checking algorithm. So that we saw initially, right? Given initialization for A, B, C, D, E, F, you can put it into the expression and solve it in polynomial time. So right? So therefore I can say SAT is a NP class problem. Okay, fine. So this is done. Now see,
So
let
it
me,
looks like solution exists, but it is not generalized.
it's not generalized. Yeah.
Yeah.
Now let me tell this. If I give you Dijkstra's algorithm, let's say Dijkstra's algorithm, it is a P class problem, right? Because it is E log V, some E log V time it takes. Or you
Yeah.
take, yeah, so let's take example of Dijkstra. Dijkstra is P class problem, E log V. Now I give you a graph, a Dijkstra graph, right? And I give you a particular path, right, between some source vertex to some destination vertex. I give you from A to D I have to reach, and the path that I follow to reach from A to D is this path, A, C, B, D, some particular path I give you. And I give you the graph, I give you the path. And I tell you to verify whether this is the shortest path or not. Can that be done in polynomial time, or will it take exponential time?
Polynomial time.
Simple polynomial time, you traverse the graph and check whether my answer is correct or not. So this is what, I mean, the algorithm that you will write is you will traverse the graph and you will check the path that I have given is the shortest path or not. That can be done in polynomial time, right? Any graph traversal you can do. So that means, what are you doing? It's checking, right? I gave you the Dijkstra. I told you I have to find shortest path, and I also told you this is the source and destination and this is the path. All you did was check whether the path is the shortest path or not, whether it is shortest or whether it is not shortest, whether some other path exists with a shorter value. So that means you verified. You check whether the given answer, whether the answer that I've given is actually a following Dijkstra, right? That's what you checked. So that is a checking algorithm. So, and it took you polynomial time to write that checking algorithm. So then what is happening? I told you the definition of NP class is any problem for which polynomial time checking algorithm exists. Now for Dijkstra also, polynomial time checking algorithm do exist, definitely. But we know Dijkstra's time complexity is E log V, which is again polynomial time complexity. So we know Dijkstra belong to P class. So what does this mean? Does Dijkstra belong to NP class also? Getting the point? Getting the point, what I'm trying to say?
Yes, sir.
I mean, I'm not asking you whether it belongs to which class. I'm asking you the dilemma. Are you getting the dilemma, what I'm trying to say? NP class definition is polynomial time verification algorithm must exist. Done. P class definition is those problems which are solvable in polynomial time. Okay. Dijkstra takes E log V time, which is polynomial time. So Dijkstra belong to P class. Okay. Now I give you the Dijkstra graph and a path and ask you to verify whether this path is shortest path or not. It would take you one traversal to find whether it's shortest path or not. Traversal of a graph is polynomial time. So basically you are verifying whether the path that I give you is the shortest path or not, which is essentially a verification algorithm. And you traverse the graph to verify it, which is a polynomial time algorithm. So your verification algorithm is taking you polynomial time to verify my answer of Dijkstra is correct or not. So that is the definition of NP class, right? The verification algorithm of polynomial time. So if that is the case, then Dijkstra is satisfying the NP class definition. But we know Dijkstra's complexity is E log V, which is polynomial time. So then Dijkstra belongs to P class, or does Dijkstra belong to NP class?
P class.
But NP class definition is also very satisfying, right?
It is satisfying, but whenever
you are using as of now, right?
As of now was with us now. Wait, as of now was when I said that all those problems which are not solvable in polynomial time as of now belong to NP class. When I told you in terms of the problem's time complexity, but when I'm telling you in terms of the checking algorithm, that is the valid definition. That is the definition of NP class. NP class definition is all those problems for which polynomial time checking algorithm exists. This is fixed. This is now also it is fixed. But if I try to tell you the simple definition of NP class, then I have to use as of now. The simple definition is what? NP class, therefore it is NP time. That is basically all problems which are not solvable in polynomial time are belonging to NP class problem. When I'm using this when I'm using this definition, then I would say as of now, because that's not a definition, that's an observation. Definition, I would say, in terms of checking algorithm, that is the correct definition, and that holds now. That holds 100% now. But I am telling you in terms of the correct definition of NP class only. The checking algorithm takes polynomial time. Any algorithm you take, I don't worry what its complexity is. I am worrying what is the complexity of its checking algorithm. If its checking algorithm is polynomial time, it belongs to NP class. That's the definition of NP class. So now I picked up Dijkstra and I told you to verify it, and you verified it in polynomial time. So its checking algorithm is done in polynomial time. So then Dijkstra belongs to NP class.
According to the definition, maybe yes, is dilemma. But
It's not dilemma. When you are following a definition, then you have to follow. Definition means it's correct.
yeah, it's correct then. Yeah.
So correct. Actually, it belongs to NP class.
Oh,
But Dijkstra belong to, then what is the definition of P class? P class is saying it belongs to P class because it's a polynomial time. E log V, we know Dijkstra's complexity is E log V. E log V is polynomial time, right? So it belongs to P class also.
maybe it is belonging to both.
Confusing, sir. Actually, we are not able to bifurcate both the statements.
Oh, P class is subset of NP class. Got it, sir.
Okay.
Yeah.
It's not confusing. It's actually the inference that you get. If you have these two definition, what does it infer? It infers that, yeah, Dijkstra is part of P and Dijkstra is also a part of P, NP. And how is it possible? Because a P is a subset of NP class. Why? Because there would be some algorithms in NP class, which is over here. Let's say outside
So
P.
this is for the all cases, na?
For all
All
cases.
the P classes, all the P cases are the subset of the NP class, universally.
Yeah, universally. This is the problem of, this is your
Yeah.
universal problem.
Yeah. Got it.
Okay. So what does that means is, obviously, see, you missed main, what should I say, the simple path, the simple point of this whole discussion, that if most of the intractable algorithm, the exponential time algorithm, right, some satisfiability problem which has 2 to the power n possibilities or something like that, which is taking you exponential time, we have polynomial time checking algorithm for exponential time algorithm, right? If we have polynomial time checking algorithm for exponential time algorithms, then obviously we would have polynomial time checking algorithm
One second. What do you tell?
for exponential time algorithm, like the satisfiability algorithm. We had
Yeah.
polynomial time checking algorithm, isn't it? We discussed that.
Yeah.
So
Yeah.
I have polynomial time and checking algorithm for exponential time algorithms, right? To check the exponential time algorithms, when an answer is given for that exponential time algorithm, I can write a polynomial time algorithm which would check whether the answer is correct for that exponential time algorithm or not, right?
Yeah. Correct.
If that is the case, then if the main problem is polynomial time, then obviously I can write a checking algorithm which is polynomial time. When the main problem is exponential, then also I can write a polynomial time checking algorithm. So if the main problem itself is polynomial time, then obviously I can write a polynomial time checking algorithm, isn't it?
Yeah.
So if that is the case, then definitely all P class problem, that is all P polynomial time problems, must lie inside the NP class, because the definition of NP class is all those problems for which polynomial time checking algorithm exists.
Has been exist. Yeah.
Right? So P is a subset of NP. As of now, this is the observation. The $1 million problem is, the holy grail is,
$1 million problem.
okay, whether NP is equal to P or not. That's the $1 million problem.
No, it is not equal.
Oh, then you should get $1 million. You have to prove it, whether it is equal or not. It's not proved. We don't do anything.
Not equal.
No. See, I am telling you this subset thing, na, NP and P. I mean, this is not anything fixed. This is the understanding as of now. Whatever I'm telling you over here, this is the core understanding as of now. But whether NP is equal, I am now stating that NP. So basically, P is a subset of NP. This is the understanding till now. Okay, but whether is this understanding till now 100% correct? It is correct. NP is a subset of P is a subset of NP. It is correct. But whether P is a subset along with equal to NP, is this okay or not? That we don't. Okay, I mean whether it is a strict subset or whether it is not a strict subset, right? That is unknown. Okay, as of now, forget that. If all of
This statement is correct. P is a subset and equal to subset equal to NP, but it is not always correct.
no. See, the thing
Because
is, we don't know. I mean, it's not 100% verified. This strict subset, this strict subset notation is correct or not. We don't know 100% as of now. Okay, so as of now,
no, this one is correct. No, P is a subset of NP is always correct. No,
P is a subset of NP is correct. So let's say there can be two
but
possibilities.
P subset and equal to of NP is not always correct.
It may or may not be correct. That we don't know yet.
It may or may not be. As of now, P is subset of NP.
Yeah.
But as of now, P is not subset equal to NP.
Exactly.
Am I right? Yeah.
Exactly. That's the point.
Correct.
Okay.
Yeah.
So let's take a problem from here. If I take a problem, let's say this problem is problem A, and this problem that I take from here is problem B. So what is the difference between A and B? For A, solving A takes polynomial time.
Polynomial time.
Verifying or checking a solution given for A takes polynomial time, which is basically my verification algorithm. For
Correct.
B, solving B takes exponential time
As of now.
as of now.
As of now, yes.
Verifying a solution given for B takes
Takes polynomial time.
100% confirm, not as of now. Okay.
Yeah, it is 100% confirmed here.
Okay. So this
Yeah.
is the difference between NP and P and all these things. And now we would discuss another aspect of it, which is a practicality aspect. Now, NP and P is done. Practicality aspect is how these classes are helpful in two very important situations. The situation number one is to prove a problem is intractable. Number two is to solve a problem for which we don't know the algorithm. Isn't this magic? The second one, to solve a problem for which we don't know the algorithm. We don't know the algorithm, but still we would be able to solve it using some trick.
Yeah. Trial and error.
No, not trial and error. By using some other algorithm. Okay, we would see that.
If algorithm does not exist, how can you go for the other?
I'm not saying algorithm does not exist. I'm saying I don't know the algorithm. Don't know.
Okay. Yeah. We don't know the algorithm.
We don't know the algorithm. Okay. To prove, okay, as of now, just move this concept of algorithm does not exist from your head, because that is for undecidable problem. Okay, that we are not.
Yeah.
All these problems, algorithm exists, answer exists, everything exists. But the time taken for that is more or less. If it is more, it is NP. If it is less, it is P. Less means polynomial time. Okay.
Yeah.
So there are two new missions that we got. First is to prove a problem is intractable, and the second one is to solve a problem for which we don't know the algorithm. Now, what is the meaning of to prove a problem is intractable? See, we can get into some situations where we are trying to solve a real world problem, and we are trying to find an algorithm for that problem, and by beating our head for 2-3 months, we still couldn't find a proper algorithm to solve it. So trial and error we can do. I'm not saying it does not exist. Obviously, I am saying some algorithm will exist, but I am not able to find it. Okay. So we can do trial and error, but trial and error would give me exponential time, right? Because that many cases would be there. So now how can you convince your group lead or tech lead or your manager or whoever, basically your professor if you are in academics, how can you convince or that, okay, I am not able to find it, but I can be sure that no one else will also be able to find this. I am not able to find a proper algorithm for this problem, but I can surely tell you this problem's algorithm is not easily polynomial time solvable algorithm does not exist. Acha, when I'm saying I'm not able to find it means I'm not able to find a polynomial time algorithm. Okay. Exponential algorithm you are doing brute force. That would take exponential time, then it would work. But what I'm trying to say is I am not able to find a polynomial time algorithm. That's why the question is this: to prove a problem is intractable. Okay, so that is non-polynomial. So I'm not able to find a polynomial time algorithm, but I'm not able to find it because no one else will also not be able to find a polynomial time algorithm. If I have to prove this, I have to convince my professor or my in an industry setup, I have to convince my product manager that okay, we are not able to do it because we cannot do it. No one can do it in polynomial time, right? If you have to convince this, how can you do that? So then we come into a new concept. Both of these things can be done by using a new concept, what we call a reduction. Okay. And in discourse, we had some doubts on this topic of reduction. What is meant by reduction and all. This is a fairly difficult topic and fairly complex and theoretically heavy topic, but we would do it on a very upper level and from a very not definition, but for a very postulate kind of way. We would just learn a few rules and postulate, and we would follow them and stick to them. Just this much, okay? Don't go into the details of these things. So what are these? What is reduction? We would now jump into that directly. Reduction essentially means you are converting a problem into another. Given a problem A, you are converting that problem into B. Now, what is the meaning of this vague thing, right? Problems are something very different thing, right? How can you convert a problem A into problem B? The concept is I would try to represent all the inputs of problem A in a format. I would make some changes to the inputs of problem A in a format so that they represent the inputs to problem B. Okay. So, for example, let's say so let's say I have this Boolean expression x. You guys have not done propositional logic, right? Are these signs known to you? Something like this.
We did some of this in DBMS. So yeah.
DBMS would be very, very less, I think.
Like we know what these mean, like or, and not.
Okay. Okay.
We did not use it. I think only for all we used.
Yeah, in DBMS, I think in tuple relational calculus or domain relational calculus, a little bit was there, but I don't think.
Not all.
Yeah.
It was not used. Just notation, one or two notations it was used.
Okay, fine. Let's not go into all of this. Let's finish up the main part. Okay, so what is reduction means? I would convert a problem A into problem B. And how can I convert it? Okay. Can you mute, please? The background noise is coming. Yeah. Convert all inputs of problem A into a format so that they represent so that they represent input to problem B. If you can somehow convert the problem, the format, the input format, the format of the input of problem A, make some changes into that while retaining the main characteristics of the input, right? If you can do that, so that that new change in format has transformed the input into another format, which is actually the same format as the input of B problem. So then you can use this input to put into the B problem, and B's solution you know, suppose. Okay, suppose B's solution you know, right? Then what you can do is you can actually, there is a little bit difference over here. I am telling you, let's say you know the algorithm for A. Sorry, you know the algorithm for B. Okay. Know the algo for B. Suppose you know the algo for B. So if you can convert all the inputs of A, and for A you don't know. Don't know. So at first I'm addressing point 2 over here. Point 1 I would again come back. I think I left it in between, that how can you prove to your guide or your product manager that if I cannot do it, no one else can also do it in polynomial time. That part I am coming to a little bit late. As of now, I'm at first addressing this part. That is, if I know the solution to a particular problem and there is another problem which I cannot solve, then I can use the solution of the problem that I know to address the problem which I don't know. How to do that? The A is the problem whose solution I don't know. B is the problem whose solution I know. I would try to reduce the problem. This is reduce, right? Reduce the problem from A to B. What is the meaning of reduction? The meaning of reduction is I would try to convert the input of problem A into another format so that it resembles the input to problem B. Okay. Now once I can do that, sorry. When I know the problem B, I have to do it in the other way, right? Convert all inputs of problem A. Yeah. Okay, fine. So into a format so that they represent the input to problem B. So now use problem B on the inputs to get answer. Finally, reverse map these answers of problem A, these outputs of B into a format which resembles output of problem A. Okay, so this is the technique. A's algorithm I don't know, B's algorithm I know. If I can reduce A into B by using this concept of converting the input of A into a format that represents the input of B, then I can put the input of B and then solve it, and then the answers that I get, I would reverse map the answers of B into another format. I'm just going back now, right? So reversing back the output of problem B into a format so they resemble the output of problem A. So then I get the answer to problem A without knowing the algorithm of problem A, by knowing the algorithm of problem B. So this is one use of reduction. Now in the lectures you would see some, just a little bit of discussion is done on how to convert one problem. Some example, 2 examples are taken, I think. Independent set, vertex cover, and clique example is taken, I think. So you can check that out, but it's not very, because it's theoretical and subjective, we cannot put it in the exams. You can check that out for understanding what do I mean, but the essence is this. This is the overall idea. We know the solution for one kind of problem. We convert the unknown problem's input into another problem, and then we solve it, and then we reverse map it. But obviously you cannot do it for any possible problem. Some kind of problem will happen and some other problem you cannot convert, right? Or you cannot reduce. Essentially amount to solve problem A in, Nikhil, what are you saying? Doesn't it essentially? I couldn't read it. Essentially amount to solving problem A in polynomial time using exactly. Okay. Yeah, provided that you know a polynomial time solution to problem B. Exactly. So if you know a polynomial time, in fact, that is one of the important observation, that if you know a polynomial time algorithm for problem B, then obviously you can write a polynomial time algorithm for problem A. And that polynomial time algorithm for problem A need not be an exclusively separate algorithm for problem A. All you have to do is, so basically what I mean is, let me write it in red color. Nice observation over there. That was the next point that I was coming to, which is if I know if B has a polynomial time algorithm to solve it, then A definitely has a polynomial time algorithm to solve A. Fine. So this is a very important statement. If B, and please keep in mind, I'm reducing A to B. This arrow direction is very important. If you reverse it, if you write B to A, then the whole thing changes. This is wrong when I'm following this condition. Okay. Please keep in mind this direction of the arrow. These are very important in this concept. When I reduce A reduced to B, A reduced to B, and I know the solution of B, then only I can go for solution of A. Vice versa is not correct. Okay. And yeah, if B has a polynomial time algorithm to solve it, then A definitely has a polynomial time algorithm to solve A. But if I say it the otherwise, if I say that, okay, you convert A to B, right? You reduce A to B, and I now tell you that A has a polynomial time algorithm. A has a polytime algorithm. But does that mean B has polytime algorithm? That's the question. The answer to this question is no. I don't know. I cannot guarantee. Okay, but the other way I can guarantee. If B has a polytime algorithm and A is reduced to B, then I can guarantee A will also have a polytime algorithm, which I told just over here. When this is happening, this is the case. But the vice versa is not correct. This is not correct. Okay, A reduced to B, and I know that B has a polynomial time, A has a polynomial time algorithm, and I'm reducing A into B. If I'm doing that, can I guarantee anything about B? No, I cannot guarantee. I cannot say that B will also have a polytime algorithm. I don't know. It may or it may not have. But if I'm converting from A to B or reducing from A to B, and I remove this thing and tell that, okay, B has a polytime algorithm, that is for sure. And if it is so, will A have polytime algorithm? Right? Then yeah. Then yes.
Then yes.
Okay. In internet, in many books, in ChatGPT, in many other places, this concept is given totally wrong. Do not see it. If you really want to follow some standard book, follow Corman or the books that has given in our course announcement webpage. Check over there, Corman CLRS book, right? Introduction to Algorithms. Check that book. That is the best book in this theoretical correctness part. Or you can check the other book, which is Kleinberg and Tardor's. That is also good. But yeah, I would stick to this core textbook. Do not check some material randomly from outside. Do not check any random video. Do not go for any random PDF. This concept is very theoretical, and therefore it is given wrong in 90% of the places. So be careful, follow authentic sources to read this. So I would suggest don't go beyond Corman. Whatever is written in CLRS, follow that, or whatever we are trying to discuss in live sessions. Okay, so this thing is done. So this is my problem 2 is solved. Now I have not yet completed the problem 1, that how can I prove This is not about knowing an algorithm and solving something. Rather, now I am trying to prove that, okay, this problem which I'm trying to solve is so difficult that I cannot solve it in some, I cannot solve it in polynomial time. And I cannot solve it because no one else also cannot solve it in polynomial time. So this is the next problem that we have to now tackle. Now, how can we do that? Let's see that. Okay, so
Sir, this sheet you will share somewhere.
what sheet? Oh, this one. No, I'm deleting and writing. No, in the session, you can check on YouTube. You can pause it and check whenever
Okay,
you.
okay, okay, okay,
Yeah.
okay, okay.
Fine. So the next thing is this target one or first question. Now, how can we do it is, so again, reduction. I told you reduction is the answer for both these things. Now, in the first case, we use reduction and we had the example. Let me just write it because I have to contrast a point. So here the reduction was used A reduced to B. We know polytime algo for B. A is reduced to B, then I can, since B has polytime algo, A can be solved using it. Okay. So this is the reduction in polynomial domain part. Now, in order to prove intractable, we would use reduction in intractable domain part. So what do we mean by this? So here we had this polynomial time, right? Reduction, but this was in polytime. Now I would use reduction to address intractable situations. So let us see how that works. So same thing, let's say a problem A is there and I'm reducing A into B. So A is reduced to B or B is reducible from A. Both of these statements would be used. Be careful while you read the statement in your questions. A is reduced to B or B is reducible from A. Both these kind of statement can come. So all you have to do is figure out the direction of arrow. So A arrow B is the case. Okay. Now I tell you that when you do this reduction, right? Now it's very, very important. Okay. This is the most important part with respect to this discussion. When I am doing a reduction from a particular problem A to another problem B, always what happens is B is harder than A. This is the, I think this one line is the most important line with respect to complexity classes. When I reduce a problem A into another problem B, then the problem B is always harder to solve than A. Okay? Always harder. Whatever amount of hardness is there to solve A, B would be harder to solve. This will happen always. So let's apply this new postulate to our this discussion where we had. We told that B has a polynomial time algorithm.
How can we say it will be always harder?
Forget about that again.
Okay, okay,
Postulate. That's why
okay,
I told postulate.
okay.
Right? So just assume that when I'm reducing a problem A into another problem B, then B is harder than A. Okay. Now, if B is harder than A, now let's apply that concept in this discussion, the initial discussion we had. What was the initial discussion? Initial discussion was stating A is reduced to B, okay? And we know a polynomial time algorithm for B. That was the whole concept, right? And again, we know according to a new rule, since A is reduced to B, B is harder than A. Right? In this case, B is harder than A. So if B is harder than A and B has a polynomial time algorithm, can I say A will always have a polynomial time algorithm? Right, correct? That's what it is. So that's why we can write this. Okay, and that's why if some other source tell you that when the opposite way, right? When I told you that if A is reduced to B and I know a polynomial time algorithm for A, I know polytime algo for A. But does that mean I also have a polytime algo for B?
No.
Why?
Because B is harder than A.
Got the point now? Why it is wrong? Okay.
Yeah.
So therefore, we just cross-verified our previous learning with our new learning. That A is reduced to B means B is harder than A. Okay, so if I have to address this question over here, I must have the algorithm for B at first and try to convert A into B. Okay, it's not that you are trying to see the problem. Why I'm saying this is many places you would see it. What they say is some problem I have, I don't know the solution to the problem, but I have another problem whose solution I know. Okay, I mean how to solve it, not solution, I mean algorithm. The algorithm I know. So what I would try to do is the solution for which I do not know the solution for which I do know the solution. The problem for which I do know the algorithm. I would use that algorithm. I would use that problem to convert into the problem in which for which I don't know the solution. So basically, if I know the solution for, let's say, some problem alpha, and I do not know the solution for some problem beta, then what I would do is I would try to convert beta into alpha. That's not the correct approach. Actually, you have to do the opposite thing. If you don't know the whatever problem for which you do not know the solution, okay, so you have to convert that problem into the problem for which you do know the solution. Then only you can do that. If you do it in the opposite manner, it's wrong. Keep that thing in mind. Now let's come to this part. A is reduced to B means B is harder than A. Now if B is harder than A, and I tell you that let's say B is in NP class. Okay, forget about class. Okay, we would come to that later. So B is harder than A. Now, what was our intention? Our intention is our manager is there or our professor is there and he has given me a problem and I have to prove to him that I'm not able to find a polynomial time algorithm because it does not exist. So what would I do? How can I do that? I know B is harder, right? In this respect, I know B is harder problem. So let's say I pick up a problem from literature which I already know to be a problem of NP class. That is the intractable problem. So pick a problem which is intractable. That is belonging to, let's say, NP class. Okay. And that problem, and then let's say that problem is A. Okay. And then you convert or reduce A into my problem, which I am trying to solve, which is B. Right? If I can do this reduction successfully, right? If I can do this reduction successfully, if I can reduce successfully, what can I guarantee? I can guarantee B is, or my problem which I'm trying to solve, at least as hard as A. B is at least as hard. It can be more. It can be harder. It is at least as hard. It can be more harder. I mean, more harder. That is harder. It can be harder than A also, right? So what I would do is I would pick up a problem which I already know in literature to be belonging to NP class. Let's say SAT problem, or there are multiple other problems are there which belongs to NP class. A traveling salesman problem, clique problem, circuit SAT problem, 3 SAT problem, horn SAT problem. There are multiple things are there. Okay. Vertex cover problem. So I can pick any one of the problem from the NP class, and all I have to do is convert that problem into my problem, right? Reduce that problem into my problem. If I can do that, then I can guarantee that my problem is more hard, I mean harder than this problem, or at least as hard as this problem. And this problem is anyway NP problem. That means my problem is actually, it is also very difficult to solve, and that's why not only I, no one else as of now would be able to solve it. So that's how we can convince our professor or tech lead or whoever it is, right? So that this is the practical aspect of using this reduction. Now, what kind of question might come from this point of view? That okay, before coming to the question part, let me just briefly mention 2 other new classes. Okay, we have yet known a P class and NP class. Now there are 2 other new classes which might come into the questions in exams. So we call this B problem, right? B problem is harder than A when I am reducing A into B. Let's say we discuss something. Let's go to this diagram. Now let's say what I do is I pick up all the problem which are there in NP, right? All the problem which are there in NP, all the problem. Pick all the problem which are there in NP. I want to ask you a question that give me such a problem which is harder to solve than any of these problems. Which is harder to solve than any of this problem. How can you do that? So the thing is, if I pick, so when I'm saying you that let's say some problem alpha is there, okay, I don't know where this alpha belongs as of now. Some problem alpha is there, and that problem must be harder or at least as hard as any problem in NP. So that means what? I have to write for all problems in NP, right? For all, let's say, write it in this manner. For all X element of NP, X is basically the problems in NP, I must be able to reduce X into alpha. That would ensure that alpha is harder than all the problems in NP, right? Such a problem which is harder than all the problem is in NP is called NPH or NP hard problem. Okay, NP hard problem. Fine. So any problem you take, all the problem can be reduced. So for all X element of NP, X is the problem in NP, X must be reducible to alpha. If that is the case, then alpha belongs to NPH class, NP hard class, and NP hard, and therefore alpha is an NP hard problem. Now, where is the existence of this NP hard class? Where does it exist in this set diagram? That is the next question. The thing is, see, NP hard problems which we have, some of them problem might have a polynomial time verification algorithm, and some of those problem might have an exponential time verification algorithm. That is, all the NP hard problem that is we have, I mean, all the problem which are NP hard, at least in literature, whatever NP hard problems are there, we have observed that some of those problems can be checked or verified given their solution. One of the solution can be verified whether the solution given is actually the solution for that NP hard problem or not. That is the verification algorithm or checking algorithm for that NP hard problem can be doable in polynomial time. And some other NP hard problems are there for which the verification algorithm is actually taking exponential time. Even the verification algorithm for those problems are not doable in polynomial time, right? So therefore we don't know. So that means what? Some of the NP-hard problems do not have polynomial time verification algorithm, and some NP-hard problem do have polynomial time verification algorithm. So for those problem which do have, for those NP-hard problem which do have polynomial time verification algorithm, that means what? They also belong to NP class, because NP class definition is what? Polynomial time verification algorithm, and that's it. That's the only condition for being inside NP class, polynomial time verification algorithm. So some of the problem in NP hard class for which polynomial time verification algorithm do exist, they also belong to NP class. And some problems for which polynomial time verification algorithm do not exist for the NP hard problem, they do not belong to NP class. Therefore, the diagram looks something like this. I just forget about this red dots. Okay. The diagram looks something like this. And this intersection part, right, which has polynomial time verification algorithm. Okay, so this whole green is NP hard. Whole green is NP hard. Now, that part of the NP hard for which polynomial verification algorithm exists, that also overlaps with NP class, because that is the definition of NP class. And therefore, this part, this overlapping part, is what we call NPC or NP complete class. So NP complete is essentially NP plus, not plus, actually it is intersection. NP intersection NP hard. Or in other way I can write it as which has characteristics of both NP and NP hard. Fine. So this is your NP hard class, NP complete class, this intersection part. This is your NP hard class, this red color one. Okay. This is NP and this is P. So NP hard means all those problems which are at least as hard as all problems of NP. Whatever problem you pick up from NP and you pick up a random problem from NP hard, so all the problems of NP class would be less difficult to solve than the problem in NP hard class. That's why it is hard. That's why we call NP hard. And some of the NP hard problem for which polynomial time verification algorithm exist, they are called the NP complete class problem. And for all other problem of NP hard class for which polynomial time verification algorithm does not exist, their verification algorithm also takes exponential time, they exclusively belong to the NP hard class, which is basically this region. Okay, so that's it. Now, once this is done, let's come to this last discussion. So when I reduce from A to B, B is harder than A. Now, if I say that, let me delete all of this. And this is your format of question that would come in the exam. That number one, if A is NP class, is B NP or NP hard or NP complete or P or I don't know. Which is the correct answer? Which is this kind of question would come in your exam. Now, how to deal with this kind of question is, you have to keep only one thing in mind. That is, when I am reducing something A to B, all I can guarantee is B is harder than A. I can never say that B has a polynomial time verification algorithm. Okay, I can only guarantee A is reduced to B means B is harder than A. So if I know that A is NP class, right, and I'm reducing A to B, then B is harder than A. So Can I say B is NP? In order for B to be in NP, I know from hardness perspective, B can be in NP. B can never be in P, right? I can remove this totally because A is in NP and B is harder than A. So B can never be polynomial time. That is for sure. So the first elimination is P. It can never be the answer. Okay. Next thing is, okay, so B in NP class or not? In order to be in NP class, I must have a polynomial time verification algorithm, right? But I don't know anything about whether there is an existence of polynomial time verification algorithm when I'm reducing A to B. But whether B has any polynomial time verification algorithm, I don't know about it. Since I don't know about it, I cannot say whether B is in NP class or not. But I can definitely say B is at least as hard as A. That is, B is either at least or so basically B's hardness is equal to the hardness of A, or B is actually more harder than A. I mean harder than A. So that means what? B can be in NP hard class. So when A is reduced to B and A is in NP class, then B is in NP hard class. This is your answer. Now, if with this an extra information is given, that suppose that B also has a polynomial time verification algorithm. It has been given in the statement. Assume that B has a polynomial time verification algorithm. Then what you can say that, okay, from reduction, I can guarantee that B is in NP hard class. And with that extra statement that B has a polynomial time verification algorithm, I can also say that B is in NP class also. Now, if B is in both NP hard and NP class, what does that mean? B is in actually NP complete class. So your answer would be B is in NP complete class. Okay. So yeah, so this is it. But if we say, let's say point number 2 is if B is in NP class, what can we say about A? Can we say anything about A? See, B is a harder problem. I know B is NP, but A is a less harder problem. So I don't know what it is. Is it NP, it is P, or is it polynomial? I don't know. Less harder means I don't know how much less it is. Okay. So therefore, I cannot guarantee whether it is hard. I mean, less harder means it is NP hard to NP reduction in hardness, or it is NP to P reduction in hardness. I don't know anything. So if any information is given in terms of B, I cannot say anything about A. So the answer is I don't know. Okay, B is in NP hard and I do this reduction of A to B, then anything about A is, I don't know, what I cannot decide what I would get for A. But if A is in NP class, then B is in NP hard class. And if B has a checking algorithm of polynomial time, then along with being an NP hard problem, B also has a verification algorithm of polynomial time, which essentially means B is both in NP hard and NP, which means B is an NP complete problem. Okay. So that's it.
If B is in NP class, can't we say A is also in NP class?
You cannot guarantee that. A can also be in polynomial class because it is less in
But
hard.
if it's in P, it is in NP, right?
Which one is in P?
Like if A is in P, then it is anyways in NP.
If A is in P, then it is okay. From that perspective, you are saying, right? Okay.
Yeah.
From superset subset perspective. Okay. Yeah. So that you can say, but again, see why we cannot guarantee this. If B is in NP class, right? A cannot be NP hard. Wait, let me just check that. A cannot be NP hard because it is lesser in hardness. And so therefore, it can be either in P or either in NP. In that respect, you can say it will always in NP. Yeah, actually correct. That you can say then. But if I tell you it is in NP hard, then you cannot guarantee. Because then A can be either in NP hard or in NP or in P. Basically in NP hard or in NP. But if I don't tell you this hard, then you are correct. Then maybe you can write it as NP. Correct. If I tell that B is in NP class, then A is also in NP class. I mean, NP means it can, but NP or P, I don't know.
NP hard has some element which is not in NP class, right?
Yeah. That I already discussed, right?
Yeah, in the set.
This part.
Yeah.
See, the thing is, let me why I wrote this. Thanks for bringing it up, Archit. Yeah. So if I have this NP class, if B is in NP class, and I ask you whether A is in NP or P exclusively. So basically, NP means the part which is, suppose, from understanding point of view, not from question point of view. Question point of view, you can say that A is in NP. From understanding point of view, what I mean is in NP, the part except from P. So basically this NP minus P or P. So this I cannot guarantee. If B is in NP class, then I cannot guarantee whether A is belonging to NP minus P or is it belonging to P. It can be belonging to P or it can also belong to NP minus P. Either of these two places it can belong. So summing up both of them, you can say that it will always belong to NP class. That is correct. You can say that. But if I modify the question a little bit and tell that, okay, this is not NP, rather this is in NP hard class. B is in NP hard class. Then what can you say about A? Now you cannot say anything. Why I'm saying so is, when I'm reducing A to B and B is in NP hard, A is less harder than B, that is sure. But how much less harder is it? It can be it is less harder, but it can be in NP hard class, or it can be in NP class, or it can be in P class. Right? Anything lesser, lesser than equal to NP hard. Lesser than equal to NP hard is NP hard or P or NP. So there would be three possibilities. But when I'm saying only NP, then there can be only one possibility, because NP is a superset of P as of now. So with that understanding, say you can say that, okay, since NP is a superset of P as of now, that is the understanding. That's why A will anyway belong to NP class. That point of view is correct actually. Okay. But the dilemma is, I cannot guarantee whether it is belonging to the region of NP minus P or P. That I cannot decide. Fine. Okay. So yeah, that's it. So keep this thing in mind. And if I say, let's say B is polynomial time, then A is definitely polynomial time, because A is easier. And if I say A is polynomial time, then B would never, I cannot guarantee B is polynomial time or not. So that is one important point which we discussed over here already. These are some other points. Yeah. That's it. Any doubt? All things are done. LPP is left. LPP, I would urge you all to just go through. It's just normal checking comprehension and forming equation on the basis of those comprehension and solving it. Right. And even the solving the equation is not in our syllabus. It's just the idea is there, because solving those kind of equation takes another mathematical approach. Let's say simplex method and all those things are there, which is not there in your math syllabus, and neither it is addressed in PDSA in that way. So it's just an motivation kind of topic, but all the question mostly it would come through these discussions which we had, flow algorithm and these complexity classes. One question or two question might come from those LPP problems, but that would be just framing the equation. Given a comprehension, you have to frame the equation, and some of the options would be, some equations would be given which are the correct, which are the correctly framed equation. So that is, I think, that you all can, if you have a fundamental idea of maths, you can do that. How to convert a story into a form of equation, linear equation. That's what it is. So those kind of problem would come. Solution of LPP is not there. You can check that on your own. If you face any doubt, then you can tell us in our next session, or in the revision session, we can cover that. So that's all about week 11. And yeah, that's it. Any doubt? My goodness, 12:30.
Okay, sir. Okay, sir.
Yeah. Okay.
You broke all the records.
No, today was only one session, right? We have to complete it, I thought. So let's.
Yeah. Okay.
Thanks, everyone. That's it. And we would be meeting in, I think, revision session. Next is only revision session. Yeah. So yeah, OPP one mock. No, it's already done before the first OPP. Yeah. Fine. So I think next sessions would be revision session. All the best who are giving OPP, and for the interim, all the best. We would start the revision sessions after this. Thanks.
Revision session for OPP or revision session for the whole intern?